1. The classical world. This is reality on its default settings. The world of common sense, the one you were born into, where a thrown ball follows a perfect arc and a dropped glass shatters on the floor. It's a universe wound up like a perfect clock, governed by unwavering, predictable laws. This is the vision of reality perfected by thinkers like Isaac Newton. A grand, cosmic machine where if you knew the exact position and momentum of every single particle, you could, in theory, predict the entire future of the universe and map out its entire past. There are no surprises here, no true randomness, just cause and inevitable effect. Imagine the cosmos as a single, colossal game of pool. At the moment of the Big Bang, the break happens. And from that single instant, every collision, every spin, every movement of every planet, star, and galaxy is predetermined. The universe is simply playing out a game whose outcome was sealed from the very first move. In the classical world, there is one single unfolding story. This is the world you experience every moment. You wake up in the morning. Your feet touch the floor, which reliably pushes back. The coffee you pour falls into the mug, not up to the ceiling. Everything has a definite place and a definite state. Your car is in the driveway. The moon is in the sky. It is not in two places at once. And every choice you make, every path you take, collapses all other possibilities into a single concrete reality. The story of you has one past, one present, and one and only one unfolding future. It's a magnificent and comforting idea, and for everything you can see and touch, it's fundamentally true. But it is also a beautiful lie, or perhaps a profound oversimplification. A map that is only useful in a very specific territory, because this solid, predictable world, this clockwork cosmos, is just the surface of the water. It's the calm, intuitive, visible layer of reality. But as we begin to look closer, to zoom in past what our senses can tell us, we find that this is not the whole story. We find that we are living on the tranquil surface of a deep and impossibly strange ocean. 2. The quantum realm. This is the source code of reality. It's the place where the solid, predictable world you know, the chair you're sitting on, the air you're breathing, dissolves into a shimmering sea of pure possibility. Down here, at scales 100,000 times smaller than a single atom, the rules of our world don't just bend, they shatter completely. Think of it like this. In your world, a light switch is either on or it is off. There is no in between. It's a definite state. But a particle in the quantum realm, an electron for instance, is not so simple. Before you look at it, it isn't in one specific place. It isn't spinning in one specific direction. Instead, it exists in what's called a superposition, a ghostly blend of all its possible states at once. Imagine a spinning coin just before it lands. Is it heads or tails? The only true answer is that it is both, and neither a blur of potential. That spinning coin is the quantum particle. It's not until you reach out and slap it onto the table the moment of observation that it's forced to choose a state, heads or tails. This is the unnerving magic of the quantum realm. The very act of measuring a particle, of simply looking at it, forces it to abandon its infinite possibilities and collapse into one single concrete reality. Before you look, the electron could be anywhere. After you look, it's right there. It's as if the universe holds its breath until a conscious observer demands an answer. So, particles exist as waves of probability, clouds of what could be. They are not tiny billiard balls bouncing around. They are whispers of potential. And this single, bizarre fact that observation collapses potential into actuality is the key. It's the strange doorway through which we must pass to understand how one reality could become many. What happens to all those other possibilities, all the other potential outcomes for that spinning coin, when you force it to land on just one? Wave-particle duality. This is the bizarre, bedrock principle of quantum mechanics that says everything in the universe, including you, has two faces. It can be a solid, definite thing in a single place, like a grain of sand, or it can be a spread-out, shimmering wave of possibility, existing in many places at once. To understand this, imagine a wall with two vertical slits in it. If you throw baseballs at it, they either go through one slit or the other. Behind the wall, you'll find two distinct lines where the baseballs hit. Simple. Now, imagine sending water waves towards that same wall. The waves pass through both slits simultaneously, interfering with each other on the other side, creating a complex pattern of peaks and troughs. Also simple. But what happens when you fire a single electron, a tiny particle of matter, at the two slits? You would expect it to act like a tiny baseball, going through one slit or the other, creating two lines. But it doesn't. When you're not looking, the single electron acts like a wave. It somehow passes through both slits at the same time and interferes with itself, creating that complex wave pattern. It's as if a ghost of the electron explored every possible path at once. A ripple of pure potential. Here is where reality begins to fray. The moment you place a detector at the slits to see which one the electron actually goes through, the game changes. The act of observing, of simply knowing its path, forces the electron to choose. The ocean of possibility crystallizes into a single, definite point. The electron behaves like a well-behaved baseball again, creating just two simple lines. It's as if reality is shy. It performs its most magical tricks only when it believes no one is watching. This isn't a trick, it's the fundamental nature of your reality. Every particle is a cloud of potential until it is measured. It exists in a state of both until it is forced to become one. But this raises a profound, unsettling question. When you look and the electron chooses a single path, what happens to all those other possibilities? What happens to the wave? Do those other potential paths just vanish into nothing? Or do they splinter off, creating a new reality where a different choice was made? 4. The double slit experiment. Imagine you're standing in front of a solid wall. In that wall, there are two thin, parallel slits, side by side. Now, imagine you have a machine that fires tiny paintballs, one after another, towards that wall. Most will hit the wall and splatter, but some will pass through one of the two slits and hit a screen behind it. After firing thousands of paintballs, what pattern would you expect to see on the back screen? You'd see two distinct vertical lines, right? A line of paint marks directly behind each slit. It's common sense. Each paintball is a particle, a solid object. It has to choose a path. It goes through the left slit, or it goes through the right slit. It can't do both. Now, let's shrink this down to the quantum realm. Instead of paintballs, we're going to fire single electrons, the fundamental particles that build our world. We think of them as the universe's tiniest marbles. And to be sure of what's happening, we'll place a tiny detector by the slits, a little camera that tells us which slit each individual electron chooses to go through. So you fire the first electron. Click. The detector says it went through the right slit. A tiny dot appears on the screen behind it. You fire another. Click. Left slit. Another dot appears. You do this thousands and thousands of times, building up a pattern, one particle at a time. And what do you see? Exactly what you saw with the paintballs. Two distinct vertical bands. One behind the left slit, one behind the right. This is particle behavior. It confirms our most basic intuition about reality. An object, no matter how small, has a definite location. It exists in one place at one time. It follows a single, traceable path through space. When you watch an electron, it behaves just like a tiny marble. It picks a slit, travels through it, and hits the screen. Everything is predictable. Everything is normal. As long as you are watching, reality behaves exactly as you think it should. The electron plays by our rules. But this is where the comfortable, classical world begins to dissolve. Because the true mystery of this experiment, the part that breaks our understanding of reality, isn't what happens when you watch. It's what happens when you stop. The double slit experiment. This is perhaps the single most important experiment in modern physics, because it's where our everyday intuition about how the world works completely shatters. Imagine you have a wall with two vertical slits in it. If you stand back and fire a stream of tiny paintballs at it, what do you expect to see on the back wall? Two lines of paint, right? One for each slit. The paintballs are particles. They go through one slit or the other. Simple. Now, imagine those slits are in a barrier in a tank of water. If you create ripples, the waves will pass through JUB slits at the same time. On the other side, these two new waves will interfere with each other, the peaks and troughs adding up and canceling out. On the back wall, you wouldn't get two simple lines, you'd get a complex pattern of many lines, an interference pattern. That's how waves behave. Okay, so here's the mystery. Scientists decided to do this experiment with electrons, the fundamental particles of electricity. They fired them one by one, like individual paintballs. Logically, you'd expect two simple lines. But that's not what happened. After thousands of electrons were fired, one at a time, what appeared on the back wall was an interference pattern, the pattern of a wave. Think about what this means. A single electron, traveling all by itself, somehow interfered with itself as if it went through both slits simultaneously. It's not a particle OR, a wave, it's somehow both, existing in a cloud of possibilities called a superposition. But it gets stranger. The physicists, baffled, decided to watch. They placed a tiny detector by the slits to see which one each electron actually went through. And the moment they did, the interference pattern vanished. The electrons suddenly started behaving like good little paintballs again, creating just two simple lines on the back wall. The very act of observing, of measuring which path the electron took, forced it to pick one. The cloud of possibilities collapsed into a single, definite reality. This is the heart of the quantum mystery. An unobserved particle acts like a wave of every possibility at once. A measured particle acts like a single concrete thing. This wave behavior, this superposition, is the foundation for everything we're about to explore. It forces us to ask a profound question. If an electron can be in multiple places at once before we look, what happens to those other possibilities when we finally do? Where do they go? This is where our journey into the many worlds truly begins. 6. Superposition. Imagine you flip a coin. While it's spinning in the air, what is it? Heads or tails? Your intuition says you just don't know yet. But quantum mechanics offers a far stranger answer. Superposition is the fundamental rule that says, before you measure it, that spinning coin isn't heads or tails. It is, in a very real sense, both. This is the heart of what makes the quantum world so alien. In our everyday lives, things are definite. A book is on the shelf, or it isn't. You are in this room, or you are not. But for the fundamental particles that build our reality, an electron, a photon, this isn't true. Before it's observed, an electron doesn't have one specific position. It exists in a superposition of all its possible positions at once, like a ghostly cloud of potential. It is here and there and everywhere it could possibly be all at the same time. It's not just a lack of information. The particle is literally in multiple states simultaneously. This fuzzy, indefinite existence is described by something called a wave function, a mathematical description of all the possibilities. So what turns this cloud of maybe into a single solid is? Observation. The moment you measure the particle, the moment you look to see where it is, the universe seems to demand an answer. The act of measurement forces the particle to choose one state out of all its possibilities. The spinning coin lands. The cloud of potential vanishes. In an instant, the wave of possibility collapses into a single concrete fact. The electron is right here. This is called the collapse of the wave function, and it's one of the deepest mysteries in physics. But it raises a terrifyingly large question, a question that leads us directly to the many worlds. When you looked at the coin and it landed on heads, what happened to the possibility of tails? Did it just vanish from reality? The many worlds interpretation says no. It didn't vanish. It simply branched. In the act of your measurement, reality itself split in two. In one universe, you saw heads, and in another, an identical version of you saw tails. Superposition, then, isn't just a weird state of being for a single particle. It's the engine of creation, the mechanism that allows every quantum possibility to become its own, separate reality. 7. Before Okai, the observer effect. This is the unsettling idea that the very act of watching something can change what you're looking at. Imagine you want to measure the temperature of a single tiny drop of water, but the only thermometer you have is a big, hot, old-fashioned mercury one. The moment you stick that thermometer in, its own heat instantly changes the water's temperature. Your measurement has interfered with the reality you were trying to measure. Now, take that simple idea and shrink it down to the bizarre world of quantum mechanics. At this fundamental level, the thermometer we use to see things is often light itself, a photon. To know where an electron is, you have to bounce a photon off of it. But an electron is so mind-bogglingly small that getting hit by a photon is like a bowling ball getting hit by a freight train. The act of observation, of looking, fundamentally alters its path and its state. The most famous example is the double-slit experiment. When you're not looking, a particle like an electron behaves like a ghostly wave, passing through two slits at once and creating a beautiful interference pattern on the other side. It's in a superposition of possibilities. But the moment you place a detector at the slits to see which one the electron actually goes through, the game changes. The electron seems to know it's being watched. The wave-like behavior vanishes. It picks a single path, acting like a solid little ball, and the ghostly pattern disappears entirely. Your very act of observation isn't passive. It's an interaction. You're not just an audience member in the quantum theater. Your attention forces the actor to choose a role. This isn't about consciousness in a mystical sense, but about the physical necessity of interaction to gain information. The universe, it seems, behaves differently when it's not being looked at. This raises a profound question that sits at the heart of reality itself. If a tree falls in a forest and no one is around to hear it, does it make a sound? The observer effect takes this a step further. If no one is looking, is there even a single, definite tree at all? Or is there just a shimmering cloud of possibilities, waiting for a glance to collapse it into the world you know? 8. The wave function. This is the ghost in the machine. It's the mathematical blueprint of reality, and according to the manyworlds view, it's the very thing that contains every possible version of you. So, what is it? Forget waves in the ocean. The wave function isn't a physical thing. It's a wave of pure potential. It's a complete description of a particle, like an electron, before you look at it. But here's the strange part. The description isn't, the electron is here. Instead, it's a beautiful, complex map of all the places the electron could be, each with its own probability. The electron exists as a smear of possibilities, a cloud of maybes, all at the same time. Think of it like this. Imagine a single unplayed note on a piano. Before the hammer strikes, that note is pure potential sound. Now imagine a whole symphony, written but unplayed. The musical score is the wave function. It contains every note, every harmony, every rest, every possible interpretation by the orchestra. It holds the potential for a thunderous performance, a delicate one, or even a flawed one. All possibilities are encoded within the score itself. For decades, the standard view in quantum mechanics was that when you finally look at the electron, when you measure it, this beautiful cloud of possibilities instantly collapses. The symphony of potential vanishes, and you're left with just one single definite note. All the other possibilities just disappear. But where do they go? This question has haunted physicists for a century. The many-worlds interpretation offers a radical, elegant, and deeply unsettling answer. It says the wave function never collapses. The symphony is never reduced to a single note. When you make a measurement, reality itself splits. The universe branches. Every single possibility encoded in that wave function becomes real, each in its own parallel world. One universe where the electron is here, another equally real where it's over there. The wave function, in this view, isn't just a tool for calculating probabilities. It is the fundamental reality, and it's a reality that is constantly, ceaselessly, branching into an infinity of worlds. Schrödinger's cat. This isn't a story about animal cruelty. It's a thought experiment about the fundamental absurdity of reality itself, a puzzle box designed to break your brain. Imagine a steel box completely sealed off from the universe. Inside, there's a cat. Alongside the cat is a tiny single radioactive atom. Now, this atom has a perfect 50-50 chance of decaying within the next hour. If it decays, it triggers a Geiger counter, which releases a hammer, which shatters a vial of poison, killing the cat. If it doesn't decay, the cat remains perfectly fine, probably just annoyed about being in a box. Simple enough, right? But here's where reality gets weird. according to the bizarre rules of quantum mechanics, until we make an observation that radioactive atom isn't in a state of decayed or not decayed. It's in a ghostly, probabilistic blur of both tights at the same time. It exists in what physicists call a superposition. Think of it like a coin spinning in the air. It's not heads and it's not tails yet. It's a swirl of pure potential. And here's the terrifying leap. If the atom is linked to the cat, then the cat too must enter this quantum haze. Until you open that box and look inside, the cat is not alive or dead. It is, in a very real physical sense, both simultaneously alive and dead. Its fate is smeared across probability, a living ghost and a warm corpse occupying the exact same space. Now, Erwin Schrödinger didn't actually believe in zombie cats. He created this thought experiment as a protest. He was trying to show how the strange rules of the quantum world lead to utterly nonsensical conclusions when applied to the large-scale world we live in. He was basically screaming at his colleagues, "See? Your theory is ridiculous." The mainstream answer at the time was that the act of observation of U's opening the box forces reality to make a choice. The superposition collapses into one definite state: alive or dead. But this is where our iceberg starts to crack. A newer, far more mind-bending theory asks a different question. What if reality doesn't have to choose? What if, at the moment of observation, the entire universe splits in two? In one branch, you open the box to find a living cat, purring away. And in another perfectly real universe that has just splintered off from your own, a version of you opens the box to find tragedy. This is the doorway to the manyworlds interpretation, where every quantum coin flip doesn't just land on one side, it creates new universes for every possible outcome. The Copenhagen interpretation. Before there were infinite worlds, there was one profoundly strange idea. Reality waits for an audience. This is the original, the heavyweight champion of quantum theories, and it places you, the observer, in a disturbingly central role. Imagine a single particle before you look at it. It isn't a tiny ball sitting in one specific place. Instead, it exists as a cloud of pure potential, a wave of probability. Think of it like a coin spinning perfectly on its edge. It's not heads and it's not tails. It is a ghostly blend of both possibilities at once. This state of existing in all potential outcomes simultaneously is called superposition. Particle is everywhere it could be, all at the same time, a haze of maybes. But then you decide to measure it. You interact with it. You look. In that single decisive instant, the universe collapses that entire cloud of possibilities down to one and only one, concrete reality. The spinning coin topples over. It's heads. At that exact moment, the very possibility of it being tails is gone. Not just hidden, not shunted off into another universe, but utterly and completely erased from existence. This is the famous wave function collapse. Your act of observation doesn't just reveal the particle's state, it forces it into being. This is the unnerving logic behind Schrödinger's cat. Inside that box, the cat, its life linked to a random quantum decay, is not merely in an unknown state. The Copenhagen interpretation insists it is literally, physically, both alive and act dead at the same time, a superposition of states. Your act of opening the box forces reality to pick a lane. You don't discover the cat's fate, you're the very catalyst that decides it. So when we ask, is there an infinite number of me's? The Copenhagen interpretation gives a stark and lonely answer. No, there is only one you. Every time you make a choice, every time you observe an outcome, the other paths don't branch off. They simply vanish. They become the ghosts of a reality that might have been, but never was. It suggests a universe that is fundamentally fuzzy and uncertain, a canvas of pure probability that only sharpens into focus when you, the conscious observer, decide to look. Wave function collapse. It's the moment a quantum system is forced to pick a side. Before this moment, a particle like an electron doesn't have a definite position. It exists in a state of pure potential, a ghostly cloud of probabilities called a superposition. It's everywhere and nowhere all at once. Imagine a spinning coin, just a blur of silver in the air. Is it heads or tails? In that moment of spinning, it's not really either. It's a combination of both possibilities. The wave function is like that spinning coin holding all potential outcomes simultaneously. Wave function collapse is the act of you slapping that coin down on the table. The instant you measure it, the instant you look, the blur vanishes. The cloud of probability condenses into a single, concrete point. The coin is now definitively heads or definitively tails. All other possibilities have disappeared. They didn't just hide, according to this interpretation, they ceased to exist entirely. This is the heart of the famous Copenhagen interpretation of quantum mechanics. It suggests that reality is fundamentally probabilistic until an observation is made. But this raises a terrifyingly deep question. What counts as an observation? Does it require a conscious mind like yours? Or can a simple detector, a camera, or even a stray photon colliding with a particle cause this collapse? This is the measurement problem, and physicists still argue about it today. When you look at a quantum system, you aren't just a passive witness. You are an agent of decision. You are the hand that stops the coin. According to this view, your interaction forces the universe to abandon its infinite possibilities and commit to a single, lonely reality. This idea stands in stark contrast to the many-worlds theory, where the Copenhagen interpretation sees a collapse, a destruction of potential. The many-worlds view sees a branching. It argues that the coin never stops spinning. Instead, the universe itself splits in two. In one universe, you see heads. In another, an identical version of you. 12. The measurement problem. This is arguably the most profound and unsettling mystery in all of science. It's the point where the pristine mathematics of the quantum world crashes into the hard reality of our own experience. Imagine an electron before you look at it. It isn't a tiny spinning ball. According to quantum mechanics, it's a blur of possibilities, described by something called a wave function. It's spinning both clockwise and counterclockwise at the same time. It exists in a ghostly state of superposition, a beautiful probabilistic haze. The equations that describe this haze are perfect. They work flawlessly. But then you decide to look. You build a detector to measure its spin. And the instant your instrument touches that quantum haze, the magic shatters. The superposition is gone. The wave function collapses. Your screen flashes a result. Spin up. The electron has been forced to choose, and the infinite maybes have resolved into a single, concrete is. And here's the problem, the deep, nagging question that has haunted physicists for a century wide. What exactly constitutes a measurement? What is the magic ingredient that forces a quantum system to abandon its possibilities and settle on a single reality? Is it the size of the measuring device? Is it the act of information being recorded? Or, most disturbingly, does it require a conscious observer? Does reality wait for you to look at it before it makes up its mind? The fundamental equations of physics don't have an answer. There is no line in the math that says, and here the collapse happens. It's a rule we have to add in from the outside, a ghost in the otherwise perfect machine. This is the paradox that Schrödinger's cat so brilliantly illustrates. The cat is both alive and dead until the act of observation forces nature's hand. This is precisely the problem that the many-worlds interpretation was born to solve. It offers a stunningly simple, if mind-bending, solution. The wave function never collapses. The collapse is an illusion. When you measure the electron, the entire universe splits in two. In one universe, you measure spin up. In a parallel universe, an identical copy of you measures spin down. Both outcomes are real. The measurement isn't an act of destruction, it's an act of creation, branching reality into all its possibilities. The problem disappears, but in its place, you are left with an infinite number of views, each experiencing a different outcome. 13. Hugh Everett III. The man who looked at reality and decided it wasn't big enough. He is the reluctant father of the modern multiverse. A brilliant mind who proposed an idea so staggering, so utterly reality-shattering, that the world of physics simply wasn't ready for it. To understand Everett, you have to understand the problem that bugged him. In quantum mechanics, there was this bizarre rule. A particle, like an electron, could be in multiple places at once, a ghostly state of all possibilities called a superposition. But the moment you measured it, the moment you looked, reality seemed to force its hand. The particle would instantly collapse into just one position. It felt like a cheat. Why should the universe care if you're looking? Everett's solution was both elegant and terrifying. He asked, what if it doesn't collapse? What if, at the moment of measurement, the entire universe splits? Imagine you're at a fork in the road. The old theory said you pick one path, and the other vanishes into nothingness. Everett said, no. At the fork, you split. One version of you turns left, and an entirely new, equally real version of you turns right, in a brand new universe that just branched off from your own. Every single quantum event happening trillions of times a second all across the cosmos isn't a choice, it's a split. A constant, silent, explosive branching of realities. This means there's a universe where you took that job, a universe where you said what you really meant, a universe where you woke up 5 minutes earlier this morning and your entire day is different. An infinite number of yous living out every conceivable possibility. When Everett presented this in his 1957 PhD thesis, he was met with ridicule and confusion. His idea, which he called the relative state formulation, was seen as science fiction. Discouraged, he left academia for a lucrative career in defense analysis, applying his mathematical genius to Cold War strategy. He rarely spoke of his theory again, but the idea was too powerful to die. Decades later, it was resurrected and rebranded as the manyworlds interpretation. Today, it's one of the leading explanations for the quantum mysteries he found so dissatisfying. Hugh Everett didn't get to see his theory gain the respect it has today, but he left us with a profound and perhaps unsettling legacy. The possibility that you are not one story, but an infinite library of them. Quoi? The relative state formulation. Before it was ever sensationalized as many worlds, this was Hugh Everett's original, far more descriptive name for his theory. And buried inside this technical phrase is the elegant answer to the single biggest objection people have. If the universe is constantly branching into countless copies, why don't we feel it? Why does reality feel so stable, so singular, so utterly normal? The old way of thinking, the Copenhagen interpretation, treated the observer like a god. It said your act of measurement magically collapses all quantum possibilities into one single reality, as if the universe held its breath until you looked and then picked a result just for you. Everett found this arbitrary and deeply unsatisfying. He proposed something far more radical and yet far simpler. There is no collapse. Ever, the universal wave function just evolves according to one rule, the Schrödinger equation. Instead, his relative state formulation says that when you measure a quantum system, you don't stand outside of it and force its hand. You become woven into its very fabric. You become entangled. Picture an electron in a perfect superposition of two locations, A and B. When your measuring device, and by extension your eyes, your brain, you interacts with it, the universe doesn't flip a coin. The entire system, which now includes you, evolves into a new, more complex superposition. This new state has two major branches. In one branch, the electron is at position A, and a version of you exists who has definitively seen it at position A. Your brain, your memories, your very atoms are now correlated or locked in with that specific outcome. But in the other branch, which is just as physically real, the electron is at position B, and a different version of you has seen it there. Your state is now defined relative to the outcome you observed. This is the key. The you in branch A can no more perceive or communicate with the you in branch B than you can hear a radio station by tuning your eyes to it. The branches have decohered, they are now causally isolated worlds. There is no jolt, no cosmic shudder, because from your point of view, nothing split. Your stream of consciousness simply followed one consistent path. The world didn't divide, force you. Your interaction with the world was the division. You are always, and only ever, aware of the state of the universe relative to you. 15. The many worlds interpretation. What if every choice you've ever made and every choice you didn't make both happened? What if the universe doesn't force you down one path, but instead splits itself in two so you can walk down both? This is the core idea of the many worlds interpretation, or MWI, one of the most profound and unsettling ideas in all of physics. To get it, you first have to appreciate the problem it tries to solve. In the bizarre world of quantum mechanics, a particle doesn't have a definite state until it's observed. Before you look, an electron isn't his or their heirs. It exists in a haze of all possibilities at once. The traditional explanation, called the Copenhagen interpretation, says that the act of measurement forces reality to pick one outcome. The haze of possibilities instantly collapses into a single, concrete fact. All the other possibilities simply vanish. But in the 1950s, a physicist named Hugh Everett III asked a radical question. What if they don't vanish? What if the universe is far too elegant to just throw away possibilities? He proposed that there is no collapse. Instead, at every quantum decision point, the entire universe branches. Imagine reality is a great river. Every time a quantum event could go one of two ways, the river splits into two parallel streams. In one stream, the event went left. In the other, it went right. Both are equally real. Both continue on, splitting again and again with every subsequent quantum choice, creating a near-infinite cascade of universes. And this isn't just for subatomic particles. It's for everything. This means there is a universe where you took that job you turned down. A universe where you said yes instead of no. A universe where a slightly different firing of your neurons led you to go to bed 10 minutes ago instead of listening to this. Each of those versions of you feels just as real as you do now. They share your memories right up to the moment of the split. They aren't copies or ghosts, they are you, continuing down a different path. The MWI suggests that you aren't a single person living one life. You are a vast, branching pattern of consciousness, exploring every possible path through the cosmos. There is no the story of your life. There is only the library containing all of them. 6. No wave function collapse. This is perhaps the most elegant and audacious idea in the many worlds interpretation. For decades, quantum physics has been haunted by a ghost called the measurement problem. The standard story goes like this. A quantum system, like an electron, exists as a wave of pure potential. It's here, there, everywhere, all at once. But the moment you try to observe it, this beautiful wave of possibility inexplicably collapses. It snaps into a single, definite point. All other potentials vanish instantly, faster than light, for no clear reason. It's a messy, unsatisfying rule that physicists just had to accept. But what if the rule is simply wrong? What if the wave function never collapses? This is the radical proposal. The wave function just does what it's supposed to do. It evolves. Smoothly, continuously, governed by the elegant Schrödinger equation. There is no sudden, violent snap. So, what happens when you make a measurement? When you open the box to look at Schrödinger's cat? You don't force reality to make a choice. Instead, you become part of the superposition yourself. Your own wave function becomes entangled with the cat's. The state of you seeing a live cat and the state of you seeing a dead cat now both exist simultaneously within the universal wave function. They just can't interact with each other anymore. They have decohered. The universe has branched. Think of it like a river of reality flowing forward. At the point of a quantum choice, the river doesn't dam up and pick one channel. It splits, perfectly and cleanly, into two parallel streams. In one stream, you are celebrating the survival of a cat. In the other, you are mourning its loss. Both are equally real. You just happen to be the consciousness floating down one of these streams. The collapse wasn't a physical process happening out there. It was simply the moment your own consciousness was split, following one path out of an infinite number that were, and still are, completely real. 17. Universal wave function. Imagine a single, cosmic score of music. It doesn't just contain the notes for one melody, but every possible melody, every harmony, every cacophony, all layered together in one magnificent evolving composition. That, in essence, is the universal wave function. You're probably familiar with the idea that a tiny particle, like an electron, is described by a wave function, a cloud of probabilities for where it might be and what it might be doing. The universal wave function takes this idea and scales it up to its most extreme and logical conclusion. It proposes that there isn't one wave function for that electron, and a separate one for the atom it's in, and another one for you. There is only one, a single, all-encompassing mathematical entity that describes the quantum state of the entire universe. And when I say the entire universe, I mean it. This function includes the chair you're sitting on, the Earth beneath you, the most distant galaxy, and, most unnervingly, you yourself. Your physical body, the neural firings that constitute your thoughts right now, are all encoded within this one equation. It contains the probability of you continuing to listen and the probability of you drifting off to sleep. This is the very heart of the many worlds interpretation. Proponents like Hugh Everett argued that this grand wave function never collapses into a single outcome, the way we used to think, simply evolves. Every single possibility encoded within its structure is physically real. When you face a choice, the universal wave function doesn't pick one path. It splits. The branches. One reality forms where you turned left, another where you turned right. Think of it as the ultimate source code. It's not a program that runs and produces one output. It's a program that runs and produces every possible output, each in its own parallel thread of reality. There is no external observer to force a decision. The universe, according to this view, is a closed system, a self-contained multiverse, whose entire sprawling existence, past, present, and future, is described by this one object. It suggests that the feeling of a single, definite reality is just our limited perspective from within one of its countless branching streams. 18. Branching. Think of your life not as a single line, but as a colossal, ever-growing tree. Every moment, at the smallest, most fundamental level, the trunk of your reality splits into new boughs, new twigs, new leaves. This constant, silent, and unstoppable division is called branching. It's the engine of the many worlds. In our everyday experience, life feels like a series of choices with singular outcomes. You turn left instead of right. You order coffee instead of tea. The path not taken feels like just that, a ghost, a hypothetical. But, according to this theory, the universe never forces a choice. When faced with a quantum crossroads, it simply expands. It accommodates every single possibility by creating a separate parallel branch of reality for each one to play out. The trigger for these splits isn't your conscious decision, but the quantum world itself. Imagine a single radioactive atom. It exists in a superposition, a state of both decayed and not decayed at the same time. The moment it interacts with its environment, the moment it could be observed, the universe doesn't flip a coin to decide its fate. Instead, the universe branches. In one universe, the atom has decayed. In another, absolutely identical in every way up to that instant, it has not. A version of you exists in each. Both versions are equally real. Both feel like they are the original, the one and only you, experiencing a random singular outcome. They have no idea their twin has just been born in a parallel stream of space-time, completely and forever inaccessible. Now, scale that up. Every quantum event, everywhere, all the time, is a branching point. The firing of a specific neuron in your brain, or the one next to it. A photon from your screen striking one molecule in your retina, or another. Each is a split. Right now, as you listen to these words, a near infinite number of you are branching away from this timeline. A you who blinked a microsecond later. A you who suddenly thought of an old friend. A you in a world where a cosmic ray just harmlessly passed through your wall, and another you in a world where it didn't. You are just one leaf on an infinitely complex tree of possibilities. A single story in a library containing every tale that could ever be told. 19. All outcomes occur. This isn't a philosophical suggestion. It is the stark logical conclusion of the many worlds interpretation. It means that anything that can happen does happen. Not in a metaphorical sense. In a literal one, The universe doesn't roll the dice to decide the future. It simply plays out every single possible result across an ever-expanding canvas of parallel realities. Think of the simplest choice you can make. Flipping a coin. As that coin spins in the air, reality is holding its breath at a quantum fork in the road. When it lands, you see heads. But the universe didn't just choose heads. In that tiny fraction of a second, reality itself split in two. A whole new universe branched off from our own, where an identical you is staring down at a coin that landed on tails. Both outcomes happened. Both yous are equally real, equally convinced they are the original, now living in parallel timelines that can never again interact. You are both right. Now, let this idea sink in and expand beyond a simple coin toss. Apply it to every decision you've ever faced. That career path you abandoned, there's a version of you who is walking it right now, living a life you can only imagine. That relationship that ended? In another branch of reality, it didn't. You worked it out, and that version of you is experiencing a completely different emotional landscape today. Every what if that has ever haunted you is not a ghost of a possibility, but the concrete, lived-in reality for another version of yourself. And this splitting isn't a rare event reserved for big life choices. It's happening constantly with every quantum event in the universe. Every particle interaction, every photon hitting your retina, every neuron firing in a slightly different pattern in your brain, each one is a potential branching point. This creates an unimaginably vast, infinitely complex tree of realities. Cosmic library where every conceivable version of your life story is written and is being lived out. There are versions of you who became astronauts, artists, and versions who made one tiny different choice this morning and are having a slightly better or slightly worse day. From our limited perspective, life feels like a single, precarious thread. But from the viewpoint of the multiverse, reality is a tapestry woven from every possible thread at once. There is no chance. There is only everything. 20. Splitting misconception. When you hear about the many worlds interpretation, the image is almost irresistible. You at a quantum crossroads, literally cleaving in two. One version of you walks left, the other right, each suddenly inhabiting a brand new, freshly minted universe. It's a powerful, cinematic idea. But it's also one of the biggest misunderstandings about the theory. The universe doesn't violently tear itself apart every time a particle chooses a path. This idea of splitting implies that entire universes with all their matter and energy are being created out of thin air every fraction of a second. It suggests a constant, explosive duplication that feels more like magic than physics. If every quantum event created a whole new cosmos, where would all that energy come from? The law of conservation of energy would have a serious problem. The reality, according to the theory's proponents, is far more elegant and less dramatic. Think of it this way. Imagine the multiverse isn't a tree that's constantly sprouting new branches, but a radio receiver capable of picking up every possible station at once. Before a quantum measurement, all the potential outcomes, all the different stations, are superimposed, coexisting in a single, complex broadcast. The quantum event, the moment of choice, isn't creating new stations. It's you, the observer, tuning your personal dial to a single frequency. Suddenly, that one station comes in crystal clear, while all the others fade into what, for you, is just static. They haven't vanished. They're still broadcasting. Those other worlds, with other versions of you, are still real. You've just become decoherent from them. You can no longer interact with them or even perceive their existence. So, from your perspective, nothing splits. You don't feel a jolt. You don't feel yourself being copied. You simply experience one continuous, unbroken timeline. The you who saw the particle spin up is now on one frequency. The you who saw it spin down is on another. Each of you feels like the one and only real you, completely unaware of the other broadcasts that are still playing out, parallel to your own. You aren't being torn in two. The universal wave function is simply resolving into its distinct, non-interacting components. The term splitting is a convenient metaphor, a piece of verbal shorthand that helps us visualize an incredibly abstract concept. But it's a trap. The theory isn't about multiplication, it's about differentiation. It's not a cosmic schism, but a quiet, constant disentanglement of realities that were, in a very real sense, already there. 21. Decoherence. This is the answer to the question you've probably had your whole life. If the quantum world is a blurry sea of possibilities, why is my world so definite? Why aren't you simultaneously reading this and also not reading this? The short answer is, you are. You just can't feel it. And decoherence is why. Think of a quantum system, like a single electron, as a perfectly clear, pure musical note ringing in a silent room. It's in a superposition. A beautiful, coherent chord of all its potential states. It's both spin up and spin down at the same time. But that silent room doesn't exist in our universe. The universe is an impossibly noisy place. The moment that electron interacts with literally anything, a single photon of light, a stray air molecule, the gravitational field of a distant star, it's like a chaotic orchestra crashing into that pure note. The environment gets entangled with the electron. It listens in on its state. Imagine dropping a tiny concentrated bead of blue dye into a massive glass of water. The dye is your quantum system, a pure potential. The water is the environment. The instant the dye hits, it starts to spread. The information, the blueness, isn't destroyed. It's just shared with trillions of water molecules. The concentrated potential is lost, smeared across the entire system. You can no longer point to the original drop, you just see a glass of faintly blue water. The coherence is gone. That's decoherence. The quantum maybe of the electron gets entangled with the countless particles in its environment. The information about its superposition leaks out and becomes hopelessly scrambled, diluted across the universe. For the many-worlds interpretation, this is everything. Decoherence is the mechanism that splits the worlds. When the environment measures the electron, the universe branches. In one branch, the environment becomes entangled with a spin-up result. In another, it becomes entangled with a spin-down result. These two versions of the environment, these two worlds, can no longer interact. They have decohered from each other. The dye has mixed with the water, and you can't unmix it. This isn't a collapse into one reality. It's the permanent fracturing of reality into countless, non-communicating branches. It's the process that transforms the ghostly quantum fog into the solid, classical world you see around you. 20. The environment as observer. So, what actually is an observer in quantum mechanics? For decades, this question felt almost mystical. Does a particle in superposition only choose its state when a conscious mind, like yours, looks at it? The many-worlds interpretation offers a far more elegant and perhaps unsettling answer. Consciousness has nothing to do with it. The observer is simply everything else. Imagine you could isolate a single, superposed atom in a perfect vacuum. It's both here and there. But the moment you let the real world in, that superposition vanishes. Because the environment is constantly asking, the atom questions. A single photon of light bounces off it, carrying away information about its position. A stray air molecule bumps into it, becoming entangled with its state. Each of these tiny, seemingly insignificant interactions is an act of observation. This process is called quantum decoherence. Think of a quantum superposition as a perfect, fragile soap bubble. The slightest touch, the slightest interaction with the outside world, and it pops. The information that was neatly contained within the bubble, the particle being in multiple states at once, instantly leaks out and gets smeared across the countless particles of the environment. The different possible states of the atom no longer interfere with each other, they have decohered. For the many-worlds theory, this isn't a collapse. This is the branch point. The interaction with the environment is the fork in the road. The universe doesn't choose one path. It takes them all. In one branch, the atom is here's, and the photon and air molecule that just interacted with it proceed in a way that reflects that reality. In another parallel branch, the atom is theirs, and its environment evolves according to that fact. So, the observer isn't some special conscious being peering through a microscope. It's the universe itself, constantly taking notes. Every particle bumping into another is a measurement. Every photon that strikes your eye is an act of decoherence, splitting reality. The environment is the ultimate witness, and its ceaseless, passive observation is what gives birth to the infinite tapestry of worlds. 23. Apparent collapse. This is the central mystery that divides quantum physics. It's the moment the shimmering, ghostly world of possibilities is forced to pick a side and become the concrete reality you and I experience. Why does a particle that can be in multiple places at once suddenly decide to be in just one place the moment we look at it? Imagine reality before a measurement is a radio picking up every single station at once. A chaotic, beautiful static of every possible song, every news report, all layered on top of each other. This is the quantum wave function, a perfect superposition of all potential outcomes. Now, the old way of thinking, the Copenhagen interpretation, said that the moment you try to listen, the moment you measure, poof, all the other radio stations instantly vanish from existence, and only one remains, crystal clear. The wave function has collapsed. But how? What physical process makes everything else just disappear? It's a question that has haunted physics for a century. But the many-worlds interpretation offers a far more elegant and, frankly, stranger explanation. It says there is no collapse. Nothing vanishes. When you make a measurement, when you look at the particle or flip the quantum coin, you don't destroy the other radio stations. You simply become part of the broadcast. You, the observer, become entangled with one specific outcome. In that moment, the universe branches. You, in your branch of reality, hear the classical music station. Your wave function is now linked to that outcome. But in another branch, a perfect copy of you becomes entangled with the rock station. A third, you hears the news report. All outcomes happen. Every station continues to play. And this is the key. To you all, locked on your single branch, it looks and feels exactly like a collapse. The other possibilities seem to have evaporated because you can no longer interact with them. They've decohered from your world, becoming parallel universes that are now inaccessible, like radio signals your receiver can no longer pick up. So, the solidity of your world isn't because the other options were destroyed. It's because you are now living inside one of those options. And somewhere, in a reality that just split off from yours, another version of you is experiencing a different outcome, completely unaware of your existence, just as you are of theirs. World versus universe. Think of reality as a colossal book. A world is a single page. The universe is the entire book, binding and all. We tend to use the word world to mean our planet, our society, but in the context of the many-world interpretation, it's far more specific. A world is a single, self-consistent branch of reality. It's a complete timeline. It's the version of history where you chose to listen to this right now. Every time a quantum event has more than one possible outcome, which is happening constantly, everywhere reality splits. Each new branch is a new world, complete and just as real as our own. You are currently traveling along one of these branches, experiencing one continuous story. From inside your world, it feels like the only one that exists. So then, what is the universe? The universe is the whole structure. It's the ultimate container that holds every single one of these branching worlds. It's the tree, not just the twig you're sitting on. In physics, this is often described as the universal wave function, the total, overarching state of reality that includes every possible outcome of every event that has ever happened or ever will happen. The stars and galaxies you see in the night sky, that's just the scenery on your particular page, in your particular world. The universe is the book itself, containing the story you're in and countless others you'll never read. It's like a vast river delta, splitting into an infinite number of streams. Your conscious experience is the journey down one single stream. You can't see the other streams, but they all originate from the same river. That river is the universe. The streams are the worlds. So, the distinction is crucial. A world is a single reality path. The universe is the total physical system that allows all of these paths to exist in parallel. It holds the world where you're hearing these words, and simultaneously, the world where you fell asleep 2 minutes ago, dreaming of something else entirely. 25. Subjective experience. It's the private movie playing inside your head, a film no one else can ever watch. It's the very what it's likeness of being. Not the mechanics of how your eyes see the color red, but the actual personal experience of redness itself. It's the warmth of the sun on your skin, the specific taste of your morning coffee, the bittersweet ache of a memory. These sensations, these feelings, make up the entire fabric of your reality. They are the only things you can ever know with absolute certainty, because you are the one living them. You can describe them, but you can never truly transfer the raw experience to someone else. It is yours and yours alone. Now, here is where it gets strange when we consider the many worlds. If every quantum choice splits the universe, then there are countless versions of you, an almost infinite number. Each one of these yous is having their own subjective experience. Right now, there is a you who decided to listen to something else, and they feel just as real, just as present as you do in this moment. They are the star of their own private movie, a film with a slightly different plot. This raises a profound question. Why does your consciousness, your single thread of awareness, follow this particular path through the multiverse? Imagine your life is a great river flowing forward through time. At every junction, every choice, every random quantum event, the river splits into multiple, equally real streams. But you don't feel the split. Your awareness, like a single drop of water, simply follows one path. From your perspective, the journey is a continuous, unbroken line. You have no knowledge of the other streams, where other identical drops of you are flowing through slightly different realities. Every version of you that could exist likely does. Each one is experiencing their own unique reality, feeling their own joys and sorrows, absolutely convinced that their stream is the only one that matters. They are not ghosts or possibilities. In their world, they are the protagonist. Your subjective experience isn't an illusion. It's the lens through which you perceive your slice of this immense, branching reality. It's the anchor that makes one timeline out of an infinity of others feel like home. 26. The Born Rule. Imagine you're about to observe an electron that could be spinning up or down. In the many worlds view, the universe splits. In one branch, you see it spin up. In another, you see it spin down. Both outcomes are now equally real, existing in their own parallel streams of reality. So here's the deep, nagging puzzle. If both things happen, why does it feel like a 50-50 chance? Where does the very idea of probabilities come from when everything is guaranteed to occur somewhere? This is the mystery the Born Rule confronts. The rule itself is a shockingly simple piece of mathematics that acts as the engine of quantum prediction. It gives us a recipe. For any possible outcome, you take a number from the quantum wave function called its amplitude, and you square it. The result is the precise probability of you, the observer, ending up in the world where that outcome occurred. It is the most tested and accurate rule in all of science. But for the many worlds interpretation, it's also a profound headache. The theory itself is deterministic. The universe just branches smoothly with no randomness. So why should the numbers matter? If there's a world where your phone suddenly quantum tunnels through your nightstand, an event with an absurdly low amplitude, that world is, in principle, just as real as this one. So why are you virtually guaranteed to find yourself in a world where your phone stays exactly where you left it? The most common way to think about this is that not all branches of the multiverse are created equal. The Born Rule tells us that each branch has a certain weight or measure. A high probability outcome, like your phone staying put, corresponds to a thick, robust branch of reality. A bizarre, low probability outcome is an unimaginably thin, wispy thread. While all these branches exist, your subjective experience is overwhelmingly likely to be found on the thickest, most substantial pathways. It's not that the other worlds aren't there, it's that the quantum weight they carry is almost zero. Trying to prove why this is the case, deriving the Born Rule from the core theory itself, is one of the biggest challenges for proponents of many worlds. For now, it remains the crucial, mysterious bridge connecting the objective reality of a branching universe with the probabilistic world you actually experience. 27. The problem of probability. According to the many worlds theory, every quantum event splits the universe. So, you flip a coin, the world splits. One you see's heads, another you see's tails. Both outcomes are now real. So, what just happened to the 50-50 probability? If every possible outcome becomes a reality, then the chance of any specific outcome seems to be 100%. This, right here, is one of the biggest headaches for the entire theory. How can a universe where everything happens still have rules about what is likely to happen? Our entire understanding of physics is built on the mathematics of probability. The equations of quantum mechanics, specifically the Born rule, are stunningly good at predicting the odds. They tell us an electron is 90% likely to be here and 10% likely to be there. And when we run the experiment a million times, that's exactly what we find. But if manyworlds is true, then in every single experiment, a branch is created for both outcomes. A world where the electron is here and another where it's there. A naive look at this branching reality suggests every outcome should be equally weighted. There should be a world where a kettle of water freezes on a hot stove. But we never, ever find ourselves in that world. Why? The proposed solution is a concept called measure. Think of the universal wave function not as a single timeline, but as a vast river of potential reality. As this river flows towards a quantum choice, it doesn't split its water evenly. The mathematical amplitude of the wave function acts like the river's current, determining how much of reality's water flows down each new channel. A high probability outcome is like a massive roaring river. A low probability outcome is a tiny, barely there trickle. Yes, both paths exist, but they simply don't have the same weight, the same thickness of existence. So when that coin flip splits your reality, it isn't making two equal copies of you. Instead, think of it as the overwhelming majority of your future potential, your measure, flowing into the worlds that obey the familiar laws of chance. There might be a version of you in a universe where you just won the lottery for the 10th time this year, but the measure of that entire branch of reality is almost zero. You are statistically destined to experience a high measure world because that's where virtually all of the you is. Probability in this view isn't about predicting a single future. It's about counting the worlds and realizing that some worlds count for infinitely more than others. 28. The preferred basis problem. Imagine you're looking at a cloud. You might see a dragon, and your friend sees a ship. The cloud itself, the collection of water vapor, doesn't have a preferred shape. It's a superposition of all possible shapes. Our minds just pick out a pattern. The preferred basis problem asks a similar but much deeper question about reality itself. Why does the universe seem to prefer showing us a very specific kind of pattern? In quantum mechanics, you can describe a system in different ways, called bases. Think of them as different languages. You could describe an electron using the position basis, which tells you where it is. Or you could use the momentum basis, which tells you how fast it's moving. Quantum theory says all these descriptions, all these bases, are equally valid. The universe, in its purest state, is a superposition of all of them at once, a cosmic cloud of infinite possibilities. So, here's the puzzle. Why do you and I experience a world that seems to be written almost exclusively in the position basis? Why do you see a chair in a definite location instead of a blurry wave of momentum? Why does Schrödinger's cat, when the box is opened, split the world into a live cat branch and a dead cat branch? Why not a cat with a specific energy branch or a cat with a certain spin branch? Out of all the infinite, equally valid ways to slice up reality, why does the split happen along these familiar classical lines? The universe seems to have a preferred way of branching, a preferred basis. The leading answer is a process called decoherence. Think of a single, pure musical note ringing in a vast, empty cathedral. That's a clean quantum state. Now, let the environment in the air, the dust, the echoes off the walls. The pure note instantly interacts with everything, becoming a complex, messy jumble of sound. It has decohered. Similarly, a quantum system can't stay isolated. It constantly interacts with its environment. This relentless interaction acts like a constant measurement, forcing the system to choose the most stable, robust states to exist in. And it just so happens that states with a definite position are incredibly robust against environmental disturbance. They are the patterns that survive the cosmic noise. The preferred basis isn't a fundamental law, it's an emergent property. It's the universe, through its own chaotic interactions, deciding which shapes in the clouds are clear enough to become our reality. Einflection. Think of it as Darwinian natural selection, but for reality itself. If the answer to one of the deepest questions in the many worlds theory, if the universe is constantly branching into a near infinite sea of possibilities, why does the world you experience feel so solid, so definite, and so singular? Why is the cup on your table just there, and not in a ghostly superposition of being both there and shattered on the floor? The answer is the universe's most persistent spy, the environment. Everything that isn't the specific quantum system you're looking at, the air molecules, the photons of light, the distant stars, is constantly interacting with it, prodding it, and essentially measuring it. This isn't a passive backdrop, it's an active participant that brutally filters reality. Imagine a quantum superposition is like a delicate, complex secret. As long as it's a secret, it holds all its strange possibilities. But the environment is a relentless gossip. A single photon bounces off your cup, an air molecule collides with it, and in that instant, a piece of information about the cup's position and state leaks out. That information is copied, and copied again, spreading through the environment like a rumor, becoming entangled with trillions upon trillions of particles. This constant surveillance is incredibly destructive to the fragile, weird quantum states. A state of being here and there is an unstable whisper. The environment, by constantly listening in, forces it to shout one thing or the other. This process selects for states that are stable, robust, and can survive this endless monitoring. These are called pointer states, and they are the building blocks of our classical world. The state, the cup is on the table, is a pointer state. It can leave a consistent, redundant record of itself in the environment. The state, the cup is in a superposition, cannot. It's too fragile a secret to keep. Einselection doesn't destroy the other branches of reality. Instead, it isolates them. The information defining the cup is on the table. World gets irrevocably tangled up with itchy environment. The cup is shattered. World gets tangled up with its gone, completely separate environment. You, being made of particles, are part of one of these environments. You are entangled with just one outcome. The branches can no longer interfere or communicate. They have decohered. Einselection is the reason you only perceive one consistent story. It is the relentless, universe-spanning process that carves the solid world you know from the infinite, shimmering ocean of quantum potential. 30. Servation of energy. It's the universe's most sacred, unbreakable law. A cosmic accounting principle that states you can't create energy from nothing, and you can't make it disappear. It can only ever change its form. Think of a ball you're holding in your hand. Right now, it's full of potential energy, like a coiled spring, just waiting. When you let go, that potential energy transforms into kinetic energy, the energy of motion as it falls. When it hits the floor, that kinetic energy doesn't vanish. It converts again into the sound of the impact, and into a tiny puff of heat from the friction. The total amount of energy in that system, the potential, the kinetic, the sound, the heat, remains exactly the same from start to finish. You've just moved it from one column to another on the universe's ledger. Now, let's scale that up. This law governs the life and death of stars. A star is just a gargantuan engine for converting one form of energy into another. Through nuclear fusion, it transforms the immense potential energy locked within atoms' mass itself into the light and heat that radiates across the cosmos. The energy isn't created, it was already there, hidden in the matter. E equals mc squared is the exchange rate. But here's where this fundamental law gets tangled up in the many worlds. If energy in our universe is a fixed, conserved quantity, what happens when the universe splits? When a quantum event happens and a new timeline branches off, creating another version of you, another world, where does the energy for that new universe come from? Is the universal budget suddenly doubled? Does creating a new world violate this most basic law of physics? Some physicists propose that the total energy of the multiverse itself is what's conserved, that the positive energy of matter and radiation in a new universe is perfectly balanced by the negative energy of its space-time curvature, its gravity. A perfect cosmic zero. So, you can create infinite universes, infinite versions of you, without spending a single joule of cosmic energy. Each new world is a self-contained equation that perfectly cancels itself out. A beautiful, complex, and complete nothing. Quantum immortality. It's the chilling idea that your consciousness can never truly end because it will always follow the path of survival. Imagine a thought experiment, often called quantum suicide. You're in a room with a quantum device hooked up to a gun pointed at your head. Every second, the device measures the spin of a particle. If it's spin up, the gun does nothing. If it's spin down, the gun fires. A perfect 50-50 chance of life or death. You press the button. And nothing happens. You press it again. Once, 1,000 times. 1,000,000 times. You feel like the luckiest person alive. But you aren't lucky. This all hinges on the many worlds interpretation. This theory proposes that every quantum event with multiple outcomes causes the universe to split. A new reality branches off for every single possibility. So when you press that button, the universe splits in two. In one branch, the gun fires, and that version of you is gone. But in the other branch, the gun clicks on an empty chamber, and you survive. Quantum immortality argues that your subjective awareness, your first-person experience, is a continuous thread. It can't experience its own termination. So, your consciousness will, by definition, only ever find itself in the timeline where you survived. It's like reading a choose-your-own-adventure book where you can only turn to the pages that keep the story going. The pages that say, you have died, the end, exist, but you, the reader, can never experience them. From your perspective, you just keep making it through, against all odds. But this isn't a superpower. It's a curse. The theory doesn't protect you from aging, from pain, or from grief. It only prevents the absolute cessation of your consciousness. You would find yourself surviving freak accidents, terminal illnesses, and catastrophic events in increasingly improbable ways. You would watch everyone you love grow old and pass away. You'd witness the slow decay of your own body, trapped in a state of perpetual, agonizing survival. You wouldn't be a god, you'd be the ultimate lone survivor, forever adrift in the one timeline out of infinity where the lights, for you, just refuse to go out. 32. The quantum suicide experiment. This is a thought experiment so profound, it forces us to confront the most bizarre implication of the many worlds theory, quantum immortality. Imagine a machine, a sort of quantum Russian roulette. At its core is a single particle whose state is measured once every second. If the particle is measured in spin-up, a connected gun fires. If it's spin down, the gun just clicks, harmlessly. The odds are a perfect 50-50. Now, you are the subject. You place your head in the path of the gun, and you start the experiment. From the perspective of a friend watching from a safe distance, your fate is sealed by probability. There's a 50% chance you're gone in the first second. A 75% chance by the second. Within a single minute, the odds of you still being there are less than 1 in a quadrillion. Your friend would almost certainly witness a tragic, and very quick, end. But from your perspective, something else happens. According to the many worlds view, every time that particle is measured, reality itself splits. In one universe, the gun fires and your consciousness in that branch ends. But in another parallel universe, the gun clicks and you live to see the next second. Here is the terrifying core of the idea. Your awareness, by definition, can only follow the path of survival. You cannot experience the timeline where you die because, well, you're dead. So, what do you perceive from inside the experiment? You hear a click, then another, and another. A minute passes, then an hour, then a day. You are sitting in that chair, listening to an impossible, unbroken streak of life-saving clicks. You would be experiencing a miracle that defies all statistical logic. To you, it would feel like you cannot die. You would have proven the many worlds theory in the most personal and horrifying way imaginable. You aren't truly immortal, countless versions of you have perished in other timelines. But your consciousness is like a flame passed down an infinitely branching torch relay, always and only handed to the runner who is still moving. You are forever trapped in the timeline of your own survival, the sole remaining witness to your own impossible existence. 33. The measure of a world. If there are infinite universes, are they all created equal? Is the world where you decided to wear a blue shirt this morning just as real as the world where your car spontaneously turned into a flock of pigeons? The many worlds interpretation seems to suggest so, but this creates a baffling paradox. If anything that can happen does happen, how do we explain the reliable, predictable probabilities we see in quantum experiments? Why does an electron behave one way 99% of the time and another way only 1% of the time if both outcomes supposedly create their own thriving branches of reality? This is where physicists introduce a concept called measure. It's a way of weighing infinities. Think of it not as a measure of physical size, but as a measure of significance or probability. It's the universe's way of saying, sure, all these worlds exist, but they don't all carry the same weight. Imagine the multiverse is an infinite radio dial. Every single frequency is a possible world. You can tune into a world where you're a celebrated astronaut or one where you have wings. They're all on the dial somewhere, but the measure is the signal strength. The worlds that branch off from high-probability quantum events, like an atom decaying exactly when it's supposed to, have a powerful, crystal-clear signal. You can hear the music perfectly. These are the high-measure worlds. But the worlds born from wildly improbable events? The pigeon car world. That frequency is buried deep in static. Its signal is infinitesimally weak, a whisper lost in the cosmic noise. Its measure is practically zero. So, the version of you listening to this right now is on a strong frequency. You exist in a high-measure branch of reality. This is the world that the laws of physics bet on. While there may be an infinite number of other yous experiencing bizarre, low-probability outcomes, they are essentially ghosts in the machine, existing on frequencies so faint they are effectively unreal from our perspective. The concept of measure is our best attempt to tame the madness of infinity, suggesting that even if the multiverse contains everything, it is not a democracy. Some worlds, it seems, simply matter more than others. 34. Falsifiability of MWI. Imagine a detective who claims a ghost committed the crime. No fingerprints, no witnesses, no physical evidence. How could you ever prove them wrong? You can't. The claim is designed to be untestable. For over a century, science has operated on a core principle championed by the philosopher Karl Popper. For a theory to be scientific, it must be falsifiable. It has to make a bold prediction that, if proven wrong, would shatter the entire theory. If you predict all swans are white, finding a single black swan demolishes your claim. So, where does the many worlds interpretation fit in? This is the central, most powerful criticism leveled against it. MWI predicts that every time a quantum measurement is made, the universe splits. It predicts there are other worlds, other versions of you, living out the consequences of every possible outcome. One version of you is listening to this right now, another turned it off seconds ago. The problem? These other worlds are, by their very nature, completely inaccessible to us. They exist in a separate branch of reality, causally cut off from ours. You can never get a text message from your alternate self. You can never visit the world where you took that other job. This is the ghost in the machine of quantum mechanics. If the core prediction of your theory is the existence of something we can never, ever observe, is it really science? Or is it just a compelling piece of philosophy, a story we tell ourselves about the math? Proponents of many worlds have a clever response. They argue that MWI isn't a new theory to be tested. Instead, it's the most literal interpretation of a theory we already test every single day: standard quantum mechanics. The math, the Schrödinger equation, works flawlessly. It's the foundation of your phone, your computer, and modern medicine. Manyworlds simply says we should trust that math all the way, without adding extra unproven ideas like wave function collapse just to make the other branches vanish. So, they claim, every successful quantum experiment is indirect evidence for MWI. There are even bizarre, speculative thought experiments designed to test it, like the idea of quantum suicide. In theory, if you were hooked up to a quantum gun with a 50% chance of firing each second, you would only ever be conscious in the timelines where the gun didn't fire. From your perspective, you would become immortal. It's a prediction you could test, but one you could never report back on. It's a theory trapped in a philosophical cage, waiting for a key that may not exist. Ulti 5. Occam's razor. It's the simple, elegant principle that when you're faced with two competing explanations for the same event, the one that makes the fewest new assumptions is probably the right one. It's not about which idea is easier to understand, but which one is less cluttered. Imagine you look up and see a strange light moving across the night sky. One explanation is that it's a satellite, reflecting sunlight. Another is that it's an alien spaceship using an unknown form of propulsion. Occam's razor doesn't say the alien is impossible. It just gently suggests that the satellite explanation is a much tidier starting point. It works entirely within our existing understanding of physics and technology. It doesn't require us to invent new life forms, new interstellar drives, and new cosmic rules to make sense of the observation. Now, let's apply this razor to the very heart of our journey. The many worlds interpretation. Quantum mechanics presents a puzzle. A particle can exist in multiple states at once, a superposition. But when we look, we only ever see one outcome. Why? The traditional explanation says the other possibilities simply collapse. It's a bit mysterious, a bit unsatisfying, but it keeps our universe singular. It makes no new assumptions about the nature of reality itself. The many worlds theory, however, takes a breathtaking leap. It claims the possibilities never collapse. Instead, reality itself splits. For every quantum choice, a new, parallel universe branches off into existence. The cat is alive in one world, dead in another. You took the job in this universe, you turned it down in a near-identical copy just next door, and this is where Occam's razor makes its sharpest cut. To explain one tiny subatomic event, Many Worlds asks you to accept the creation of an entire, fully fledged universe. A universe with another Earth, another sun, another you. This isn't just assuming a zebra instead of a horse, it's assuming an infinite herd of zebras, each occupying its own separate savanna. The razor isn't an absolute law of nature. It's a philosophical tool, a guide for our thinking. It asks us, which requires a greater leap of faith, a little quantum weirdness in our one single universe, or an infinite number of universes created every single second to avoid that weirdness. It forces us to weigh the elegance of a theory against the sheer baggage it carries. 36. Ontological simplicity. What's a simpler explanation for reality? Is it one universe, governed by a set of physical laws that mysteriously change whenever we try to look too closely? Or is it an infinite number of universes, all governed by a single, unchanging, beautifully elegant law? This is the strange dilemma at the heart of ontological simplicity. You've probably heard of its cousin, Occam's razor, the idea that the simplest explanation is usually the right one. If you hear hoofbeats, you should think horses, not zebras. The principle tells us not to invent more things, more entities, than we absolutely need to explain what's going on. At first glance, the many worlds interpretation seems to be the worst offender in history. It doesn't just add a zebra, it adds an infinite herd of them, an entire cosmos for every single quantum event. It postulates a reality so vast, so bloated with copies of you, me, and everything we've ever known, that it feels like the most complicated idea imaginable. By this measure, it should be thrown out immediately. But here's the twist. The argument for ME worlds is that it's actually the simpler option. Not in the number of worlds, but in the number of rules sash. Think about it. The standard single universe model of quantum mechanics has a major problem. It needs two different sets of laws. There's the elegant Schrödinger equation that describes how quantum systems evolve smoothly and predictably over time. But then, the moment an observation is made, that beautiful equation is thrown out the window, and a violent random process called wave function collapse takes over. Why? No one knows. It's an extra rule we have to bolt onto the theory just to make it match our experience. The many worlds interpretation is daring. It says, what if we just get rid of that second clunky rule? What if the Schrödinger equation is all there is? If you follow that one, simple, unbroken law to its logical conclusion, you find that the universe must branch. The collapse was just an illusion, the experience of your consciousness following one specific path to an ever-expanding garden of forking paths. So you're left with the choice. Do you prefer a simplicity of worlds, but a complication of laws? Or a simplicity of laws purchased at the cost of an infinity of worlds? Which reality, in the end, is the more elegant design? 37. The wastefulness objection. Imagine a novelist who writes an entire epic saga with a million branching plot lines and characters just for you to read a single sentence. This is the heart of the wastefulness objection, a powerful emotional argument against the many worlds theory. It asks, why would the universe create an almost infinite number of parallel realities for every single quantum event? Why generate a whole new cosmos where you turned left instead of right just to accommodate a coin flip probability? Feels extravagant, unnecessary, a profligate squandering of reality itself. All those other versions of you living out lives nearly identical to yours, save for one tiny decision. All those universes where an atom decayed a nanosecond later. It strikes our human intuition as cosmically inefficient, a violation of Occam's razor, the principle that the simplest explanation is usually the best. Surely, a universe that collapses all possibilities into one single, tidy timeline is simpler than one that keeps every single draft. But here, proponents of many worlds flip the razor on its head. They argue that the theory is what's simple, not necessarily the outcome. The wastefulness is only in the number of worlds, not in the laws of physics that produce them. The alternative, the standard Copenhagen interpretation, requires an extra mysterious rule, that the quantum wave function collapses into one reality. Nobody knows how or why this collapse happens. It's an added complication, a patch on the equations to make the universe fit our singular experience. Many worlds, in contrast, has no patch. It just lets the fundamental equation of quantum mechanics, the Schrödinger equation, run. Think of it like a simple mathematical rule that generates an infinitely complex fractal. You wouldn't call the fractal wasteful for having so much detail. The detail is just the natural, inevitable consequence of the simple starting rule. In the same way, the multiverse isn't an extravagant choice made by the cosmos. It's the unadulterated, uninterfered with result of physics' most elegant laws playing out. The universe, from this perspective, isn't trying to save on resources. It isn't building new worlds from scratch. It's simply revealing a structure that was already potential within the mathematics. The perceived waste isn't a flaw in the theory, it's a failure of our own intuition, which is calibrated for a world of scarce resources, not a cosmos of infinite mathematical possibility. Gimme 8. The incoherence objection. This is the argument that the many worlds interpretation isn't just wrong, it's fundamentally broken. That it's not even a coherent theory because it saws off the philosophical branch it's sitting on. At its heart is one simple, devastating question. What does probability even mean if everything happens? The Schrödinger equation, the bedrock of quantum mechanics, gives us probabilities. It tells us there's, say, a 70% chance a particle will be found here and a 30% chance it'll be found there. In the classic Copenhagen interpretation, that probability is real. You make a measurement, and one outcome is chosen from the menu of possibilities. But in many worlds, there is no choice. The universe simply branches. A version of you in one world sees the 70% outcome, and another version of you in another world sees the 30% outcome. Both are equally real. So, where did the 70-30 split go? If both things happen, how can one be more likely than the other? The theory seems to be telling you two contradictory things at once. That the numbers in the equation matter, and that they don't because every path is ultimately taken. Imagine you're at a crossroads. Ein says, Path A, 99% chance of treasure. Path B, 1% chance of a swamp. In a single universe, you'd obviously take Path A, but a many worlds guide appears and tells you, don't worry, you'll split. One you will go down Path A, and another you will go down Path B. Both versions of your future are absolutely guaranteed to exist. Suddenly, the percentages feel meaningless, like flavor text. Why should you prefer the 99% path if a version of you is guaranteed to end up in the swamp anyway? The very concept of a chance seems to evaporate. This isn't just a brain teaser, it strikes at the soul of science. A scientific theory must make testable predictions. Quantum mechanics predicts probabilities. If many worlds makes the very idea of probability incoherent, then it fails to explain the experimental results it was designed to interpret. It becomes a grand story about an unobservable multiverse that can't properly connect back to the single world we actually experience and measure. Defenders have tried to salvage this using complex arguments from decision theory, suggesting that a rational you should be as if the probabilities are real. But for critics, this feels like a patch, an attempt to force meaning back into a system that has already discarded it. The incoherence objection, then, is a profound challenge. It claims that in trying to explain everything, the many worlds theory ends up explaining nothing at all, leaving us with a beautiful infinite multiverse where the rules of the game no longer make any sense. Sad. 9. Personal identity. It's the invisible thread that connects the child in old photographs to the person listening to this right now. It's the feeling of being the same continuous self, day after day. But what is that thread actually made of? What is the anchor that holds you in place across the river of time? Consider the ancient paradox, the ship of Theseus. Over a long voyage, a ship has every single one of its wooden planks replaced. When it returns to port, is it still the same ship? Now, apply that to yourself. Biologically, you are in constant flux. Almost every cell in your body is replaced over the course of a decade. The very atoms that make you are constantly being swapped out with the world around you. If you are not your physical stuff, if you are not your atoms, then what are you? A popular answer is memory. You are you because you remember being you yesterday, and the day before that, all the way back to your earliest coherent thought. Your consciousness feels like a continuous stream, a psychological chain linking your past, present, and future self. This is called psychological continuity. It's the idea that what matters is the persistence of your mind, your beliefs, your desires, and especially your memories. I am me because I have my unique story. But this idea is more fragile than it seems. What happens to someone with severe amnesia? Have they ceased to be the same person? What about a false memory, so vivid it feels real? Does that become a legitimate part of your identity? This leads some to think that identity isn't a solid object we possess. Instead, it's a process. It's a story. You are the protagonist of an ongoing narrative that you are both writing and living. Each memory is a chapter, each decision a plot twist. This story creates a sense of coherence, of being a single person, even as the character evolves. But here's where the comfortable story breaks down and where it connects to the infinite. If your identity is simply a pattern, a specific arrangement of information, memories, and narrative arcs, what's to stop that pattern from being copied? Imagine a perfect duplicate of you is created in another universe, or even in a lab. It has every one of your memories, your fears, your hopes. It wakes up, absolutely convinced it's you, with a story identical to yours right up to that moment. From its perspective, it has an unbroken claim to being you. So, which one is the real you? Or is the very idea of a single, unique you just a comforting illusion we tell ourselves to feel safe in a vast, branching reality? The self-locating problem. Imagine a perfect duplicating machine. It scans you, atom for atom, and creates an identical copy in the room next door. Both of you have the same memories, the same thoughts, the same scar on your left knee. The copy is, for all intents and purposes, UH. But you are still here in this room looking through these eyes. The copy is over there, looking through theirs. The question is, why? Why is your first-person perspective tied to this quote, is body, and not the other identical one? This is the core of the self-locating problem. It's not about finding your address on a cosmic GPS. It's about the seemingly arbitrary attachment of your consciousness to one specific physical entity among a sea of potential duplicates. And in the context of an infinite multiverse, this isn't just a thought experiment. If the many worlds interpretation is correct, or if the universe is spatially infinite, then there aren't just one or two copies of you. There are endless versions. There is a you who chose a different breakfast this morning, a you who pursued a different career, and, most unnervingly, there are likely an infinite number of yous who are, up to this exact moment, physically indistinguishable from the person hearing these words. So, what singles you out? What makes your consciousness inhabit this particular stream of reality? Think of it like a vast library containing an infinite number of copies of the exact same book. You are reading one of them. You can feel the paper, see the ink. You know you are experiencing this specific copy. But there is nothing in the book's text that explains why you are reading it, instead of the identical one right next to it. Physics can describe the book, the atoms, the forces holding it together, but it has nothing to say about which copy gets a reader. Is your sense of self just a random ticket drawn in a cosmic lottery? Is there some undiscovered property of the universe that anchors awareness to a single timeline? The self-locating problem reveals a profound gap in our understanding. It suggests that knowing every physical fact about the universe, every particle, every field, every dimension, might still not be enough to explain the most fundamental experience you have. The simple fact that you are here, now, experiencing this world from this unique, singular, and ultimately mysterious point of view. 41. Are the worlds real? This is where the theory stops being a fascinating mathematical exercise and becomes a profound, almost terrifying question about the nature of existence. When we say another world is created, what do we actually mean? Are these worlds as solid, as tangible as the one you're in right now? The answer splits physicists into two main camps. First, you have the diehards, the true believers in the Everettian interpretation. For them, the answer is an unequivocal yes. The other worlds are not lesser realities, not ghostly possibilities or mathematical fictions. They are physically real. There is another you right now who decided not to listen to this, and their world is just as valid and concrete as yours. Think of it like radio waves. In the air around you, there are countless radio stations broadcasting simultaneously. You can only tune your receiver to one frequency at a time, but that doesn't mean the other stations cease to exist. They are still there, carrying different songs, different conversations. According to this view, the other universes are simply on a different frequency. We can't interact with them, we can't perceive them, but they are fundamentally, physically real. But then there's the other camp, the skeptics. They look at the same mathematics and come to a very different conclusion. They argue that the wave function, the mathematical object that contains all these possible worlds, is not a literal snapshot of reality. Instead, it's just a tool, a remarkably successful tool for predicting probabilities. For them, the other worlds are just statistical ghosts. They represent the might-have-beens. When a quantum measurement happens, only one outcome becomes real, and the others simply vanish from the equation. They were never real places to begin with, any more than the head side of a coin is a real, separate universe when the result is tails. The other worlds exist only as abstract potential, not physical fact. So, which is it? Are you one consciousness adrift in a single concrete reality? Or are you just one version, one tune on an infinite cosmic radio, completely unaware of the endless other songs playing out in parallel? Physics, as of now, offers no way to test it. The question pushes us beyond science and into philosophy. It's not just asking about other worlds, it's asking what it means for anything to be real at all. 42. Quantum Darwinism. If the quantum world is a shimmering sea of infinite possibilities, why do you and I agree that the moon is in the sky? Why does reality feel so solid, so objective, so normal? Quantum Darwinism offers a breathtakingly elegant answer: survival of the fittest. Not for creatures, but for facts. Think of a quantum system like an electron as holding a secret. It's in a superposition. Its secret could be spin up, spin down, or a blend of both. Now, you want to learn that secret, but you're not the only one interested. The environment itself, every single photon of light, every particle of air that bumps into that electron, is also trying to learn the secret. The environment is a relentless, galaxy-sized gossip. And just like in a game of telephone, some secrets are easier to spread than others. A fragile, complex superposition is like a convoluted rumor. As the environment copies it and passes it around, the message gets garbled and lost in noise. It can't survive. But some states, called pointer states, are robust. They're simple, stable facts, like the electron spin is up e. This is a clear, simple secret. When a photon bounces off the electron, it can easily carry away a perfect copy of that fact. Then another photon does. And another. Soon, trillions upon trillions of spies in the environment are all carrying identical, redundant copies of that one stable piece of information. This is natural selection in action. The environment doesn't force the electron into one state. It simply creates an overwhelming number of copies of the most durable information available. The states that can best imprint themselves onto their surroundings are the ones that survive to become classical reality. So, when you finally come along to measure the electron, you aren't performing some mystical act of collapsing a wave function. You are simply intercepting one of the countless identical messages already flooding the environment. You're reading the headline after the story has already been printed a billion times. This is why we all agree on reality. We are all sampling from the same massive public database of information that was selected for its own stability. In the context of many worlds, the other potential realities, the ones built on the fragile, scrambled secrets, still branch off. But in our world, we experience the one that won the cosmic popularity contest. Our reality isn't the only one, but it is the one that was fit enough to survive. Deitch. He's the physicist who looked at the strange, probabilistic world of quantum mechanics and didn't just accept its weirdness. He saw it as the literal blueprint for reality. For Deutsch, the many worlds interpretation isn't some wild science fiction fantasy. It's the most rational, most straightforward explanation we have. Think about it this way. Most physicists, for decades, dealt with the quantum world by adding a special rule. They said that when we look at a particle, its cloud of possibilities suddenly collapses into one single reality. To Deutsch, this was like reading a book where millions of plot lines are developing at once, only to have the author suddenly rip out all the pages but one and pretend the others never existed. He asks a simpler, more profound question. What if the pages aren't ripped out? What if every single possible outcome just happens in its own separate parallel universe? This isn't just a philosophical preference. Deutsch grounds it in evidence. Take the famous double-slit experiment, where a single particle seems to go through two slits at once to interfere with itself. How? The standard answer is just quantum weirdness. Deutsch's answer is chillingly direct. The particle you see is being nudged by shadow particles. Particles that are identical to it but exist in these other universes right alongside ours. They can't be seen, but their presence can be felt, like a draft from an unseen window. They are the ghosts in the machine of reality, and their faint touch creates the patterns we observe. His most powerful argument, however, might be the quantum computer. We are building machines that can solve problems exponentially faster than any classical computer ever could. Deutsch asks, where is that vast computational power coming from? If a quantum computer is just one machine in one universe, it shouldn't be possible. His answer is that the computer is a nexus. It's harnessing the processing power of its counterparts across a vast number of parallel universes. Each calculation is effectively being run simultaneously by countless versions of that same machine. The other worlds aren't just a theory, they're a resource we can tap into. For David Deutsch, the multiverse isn't just out there somewhere. You're soaking in it. It's the very fabric of reality that makes the impossible possible. The fabric of reality. It's the ultimate substance of existence, the very stuff from which space, time, and you are made. To understand it, don't think of a backdrop or a stage. Instead, imagine an infinite cosmic tapestry. For a long time, we thought we understood its basic weave. Einstein showed us the canvas itself. Space-time wasn't a rigid, fixed grid. It's a dynamic, flexible fabric, like a vast rubber sheet. He revealed that matter and energy tell this fabric how to curve, and in return, the curvature tells matter how to move. A star isn't pulling a planet with an invisible rope. It's creating a deep well in the fabric, and the planet is simply rolling along the edge of that curve. This is gravity. It's the geometry of the cosmos, the large-scale pattern woven into the tapestry. But this elegant, predictable pattern is only half the story. If you could zoom in, past galaxies, past atoms, to the smallest possible scale, the tapestry dissolves into something incomprehensible. The smooth, certain threads of classical physics fray into a mist of pure potential. This is the quantum realm. Down here, the fabric isn't woven, it's constantly being decided. A particle, a single thread of reality, doesn't have a definite position until something interacts with it. Before that moment, it exists as a wave of probability, a shimmering maybe spread across the canvas. The very rules of the loom seem to be based on chance and observation. The fabric is a seething, effervescent foam where reality solidifies from pure potential only when it is measured. And here lies the most staggering implication. What if the loom doesn't just choose one path for a thread? Quantum mechanics suggests that at every one of these decision points, every time a particle could go left or right, the fabric of reality doesn't choose. It splits. It accommodates every single possibility by weaving a new universe for each outcome. This means the fabric isn't a single tapestry. It is an infinitely branching loom, a multiverse of countless parallel textiles. And you, your consciousness, your every memory, are a complex self-aware pattern woven into one of those textiles. But you are not the only pattern. In another, a version of you made a different choice this morning. In another, you pursued a different dream. Each is just as real, a unique thread in the ever-expanding, ever-unfolding fabric of all that is. 45. Quantum computation. Imagine a library with 1 billion books. A classical computer would have to check each book one by one to find a specific sentence. It's a brute force march through every aisle. A quantum computer, however, can read all billion books at the exact same time. How is this possible? It's because it doesn't compute in just one reality. Your laptop works with bits. A bit is a simple switch. It's either a 0 or it's a 1, on or off. There is no in-between. A quantum computer uses a qubit. Think of a qubit not as a switch, but as a spinning coin. While it's spinning, it's not heads or tails, it's a blend, a ghostly superposition of both possibilities at once. Now, here is where the manyworlds interpretation completely reframes what's happening. When that qubit is in its state of spinning uncertainty, it's not just a mathematical trick. It's a fork in reality. The quantum computer has, in a very real sense, split. In one universe, the qubit is a 0. In a parallel universe, identical in every other way, that same qubit is a 1. And it doesn't stop there. With just 2 qubits, you get 4 parallel universes. 3 qubits, 8 universes. With only 300 spinning qubits, a quantum computer could be performing a calculation across more parallel universes than there are atoms in the known cosmos. It's not just exploring every path in the maze simultaneously, it's literally living in a universe where each path is taken. These parallel computations aren't isolated either. They are linked by a strange, invisible thread called entanglement. This connection allows the different worlds inside the computer to interfere with each other, to whisper answers back and forth, reinforcing the correct solution and canceling out the wrong ones. So when you finally measure the result, when you stop the coin from spinning, you don't destroy the other worlds. You simply find yourself on the branch of reality where the coin landed on heads and the correct answer has been found. The other branches, the other yous, continue to exist, having seen a different outcome. A quantum computer isn't just a faster machine, it is a device that actively harnesses the multiverse itself to find answers. It is computation on a truly cosmic scale. 46. Parallel processing. Imagine you have to build 1,000 intricate Lego castles. You could tackle them one by one, a painfully slow, linear process. Or you could have 1,000 versions of yourself, each with their own set of bricks, all building their own castle simultaneously. In the same amount of time it takes one of you to build one castle, 1,000 are completed. That is the brute force elegance of parallel processing. It's not about doing one thing faster, it's about doing everything at once. In the world of computing, this is a familiar concept. Your phone, your laptop, they don't have just one brain. They have multiple processing cores. Think of them as individual workers on an assembly line. One core might be streaming this audio to your ears, while another is refreshing your background apps, and a third is calculating your GPS location. They don't wait in line. They work in parallel, creating a smooth, seamless experience. It's the difference between a single, overwhelmed chef and a full kitchen brigade where every cook has a specific task, all executed in perfect simultaneous harmony. Now, let's take this concept and apply it to the grandest scale imaginable. Reality itself. What if the universe is the ultimate parallel computer? The manyworlds theory proposes a reality that operates on this very principle. At every quantum crossroads where a particle could be here or is there, the universe doesn't force a choice. It doesn't roll a die to decide the outcome. Instead, it executes both possibilities. The entire timeline splits, creating two parallel streams of reality, each one as real as the other. Consider a simple decision from your day. You stood at a street corner, debating whether to turn left or right. In a single thread universe, you chose one path and the other became a ghost. A what if? But in a parallel processing cosmos, the universe simply allocated new resources. In one universe, you turned left. In another, a perfect copy of you at that exact same moment turned right. Neither of you is a ghost. Both are the main character of your own story running on a separate processor. This isn't chaos, it's cosmic efficiency. A way to explore every permutation of existence. The you listening to this right now is just one thread in an infinitely complex program, and countless other threads are running alongside you, exploring every other choice you could have possibly made. Or 7. The multiverse. It's the ultimate what if. The radical idea that somewhere out there, a version of you is living out the consequences of every choice you didn't make. The you who took that other job, who boarded that different flight, who said yes instead of no. This isn't just a thought experiment. It's a serious proposal born from the baffling rules of quantum mechanics, a potential answer to some of physics' deepest riddles. The most famous version is the manyworlds interpretation. It tackles the weirdness of quantum superposition, the fact that a particle can exist in multiple states at once until it's measured. The theory says the particle doesn't just pick one state. Instead, reality itself splits. Imagine reality not as a single line, but as the trunk of an infinite tree. At every quantum event, a new branch grows. In one branch, the atom decayed. In another, it didn't. This isn't a metaphorical split, it's a literal schism in the fabric of reality, creating two parallel, completely separate universes. And since you are made of trillions upon trillions of these quantum particles, you are branching too. Constantly. This leads to a staggering, almost terrifying conclusion. There isn't just one you. There are countless yous. There is a you who became a world-famous musician, and a you who became a quiet librarian. There's a you who is happier than you can possibly imagine, and a you who has faced unimaginable tragedy. The comfort, or perhaps the horror, is that no potential is ever truly lost. The road not taken was, in fact, taken by another you, and manyworlds is just the beginning of the iceberg. Other theories paint different pictures. The bubble universe theory suggests our cosmos is just one bubble in an endless, frothing sea of other universes, each one born from its own Big Bang. In these other bubbles, the fundamental constants could be different. Gravity might be weaker, light might be slower, creating realities completely alien to ours. Then there's the quilted multiverse, which proposes that space is infinite. If you travel far enough in any direction, the laws of probability dictate you will eventually find another region of space identical to ours, a cosmic twin. So, as you drift off, consider the sheer scale of it all. You are not just one story, but an entire library of every possible life you could have lived. A collection of every path, every dream, every failure, and every triumph. And perhaps, in one of those countless other worlds, another version of you is lying awake right now, staring into their own darkness, wondering if a universe like this one, a universe with you in it, could possibly exist. 48. Tegmark's Level 1 Multiverse. This isn't a multiverse of strange new physics or parallel dimensions. It's the multiverse you get from accepting one simple, humbling fact. That space is big. Really, mind-numbingly big. Potentially, infinitely big. Imagine you're on a tiny boat in the middle of a vast, calm ocean. You can only see to the horizon, a perfect circle of water around you. You don't assume the world ends there, do you? You know with certainty that the ocean continues on. Our universe is the same. There's a cosmic horizon, a fundamental boundary set by the speed of light. It's the edge of the universe we can seize, because light from any further away simply hasn't had enough time to reach us since the Big Bang, 8 billion years ago. But almost every cosmological model we have suggests that space itself keeps going, stretching on and on, far, far beyond that visible edge. Now, here's where it becomes deeply personal. Our observable universe, this cosmic bubble we can see, is enormous, but it's finite. And within it, there are a finite number of ways particles can be arranged. It's a staggeringly huge number, but it is not infinite. Think of it like a cosmic deck of cards. If you shuffle that deck an infinite number of times, you are mathematically guaranteed to get the exact same sequence of cards again. And again. Infinitely many times. Tegmark's level Y multiverse applies this exact logic to the cosmos. If space is truly infinite, and it's filled with matter and energy just like our region is, then our exact cosmic arrangement, our entire observable universe, is just one shuffle of the cosmic deck. So somewhere out there, in that unimaginable darkness beyond our sight, the same hand has been dealt. There is another sphere of space, billions of light years across, that is a perfect atom-for-atom copy of ours. In it is a copy of the Milky Way, a copy of our solar system, and a copy of Earth. And on that Earth is a copy of you, a physical twin living this exact moment. And the idea doesn't stop at perfect copies. An infinite space means infinite variations. There are countless other cosmic patches where you made a tiny different choice today. A you that skipped your morning coffee. A you that pursued a different career. Every possible variation of your life, as long as it's permitted by the laws of physics, is being played out somewhere across that endless expanse. These aren't other dimensions. They are just distant places in our own single, infinite universe. You will never meet them. You will never see them. They are other boats on the same cosmic ocean, forever beyond your horizon. Tegmark's Level 2 multiverse. This is where the story gets truly strange. It's not just about more space, like a bigger version of our own cosmos. It's about different kinds of space, born from a process called eternal inflation. Think back to the Big Bang. We imagine a single point exploding outwards. But a leading theory, cosmic inflation, suggests that in the first fraction of a second, the universe expanded faster than the speed of light, stretching from something smaller than an atom to a cosmically vast size almost instantly. Now, here's the level 2 twist. What if that inflation never truly stopped everywhere at once? Imagine a gigantic, endlessly rising loaf of sourdough bread. This is the background of space-time, constantly expanding. But here and there, tiny pockets of this dough stop rising. They cool down, they stabilize, they bake. Our entire observable universe, every star, every galaxy you've ever seen a picture of, is just one of these baked pockets. A bubble that pinched off from the infinitely expanding whole. This process is called eternal inflation. The sourdough of space between the bubbles is still inflating, still expanding at that unbelievable rate, constantly spawning new bubble universes, each one potentially as vast as our own. We are living in one bubble, completely cut off from the others, which are racing away from us faster than light. And here's what makes this a new level on the iceberg. These other bubbles don't have to play by our rules. The fundamental constants of nature, the very laws of physics, could be different in each one. Think of it like a cosmic control panel. In our bubble, the dial for gravity is set to a specific value. The dial for the speed of light is set just so. These settings allowed stars to form, planets to cool, and life, you, to emerge. But in another bubble, gravity might be 1,000 times stronger, crushing everything into black holes. In another, the forces holding atoms together might be too weak for matter to even exist. So, could there be another you in a level 2 multiverse? It's far less likely than in level 1. The fundamental recipe of reality would have to be identical. But in an infinite sea of bubbles, with an infinite number of dials being turned, almost impossible starts to look like inevitable. Somewhere out there, in a bubble almost identical to our own, a being almost identical to you might be looking up at their sky, wondering if they're alone in the cosmic foam. Level 50. Tegmark's Level 3 multiverse. Forget universes located light years away. This theory proposes something far more intimate and unsettling. It suggests that infinite other worlds are being created right here, right now, with every single quantum event. This is the famous many worlds interpretation. It all hinges on the strange rules of the quantum realm. Down there, a particle doesn't have to be here, or is there. It can exist in a fuzzy state of being in multiple places at once, a superposition of possibilities. When a measurement is made, our instruments only ever show one outcome. The electron is here, not there. The radioactive atom decayed, or it didn't. But the many-worlds theory asks a radical question. What if the observation doesn't destroy the other possibilities, but instead realizes all of them? Imagine reality not as a single timeline, but as a majestic, endlessly branching tree. Every time a quantum coin toss happens anywhere in the cosmos, the trunk of reality splits. It doesn't just split in theory. The entire universe cleaves into separate, equally real branches. On one branch, the atom decayed. On the other, it did not. And you, and everything around you, are copied onto both branches, continuing on without ever noticing the split. This is where it gets deeply personal. It means there is a version of you who turned left this morning instead of right. A version of you who pursued that dream you abandoned, who is living in that other city, who married your childhood sweetheart. There's a version of you who made every mistake you so carefully avoided, and a version who achieved every success you only ever imagined. These aren't ghosts or alternate timelines from science fiction. According to this theory, they are flesh and blood. They are you. Each one of them is living out their life, feeling just as unique and real as you do right now, completely oblivious to your existence. These other worlds aren't separated by vast distances, but by their quantum state. They are layered on top of our own reality, like pages in an infinite book, but we are forever confined to reading just one page. The Level 3 multiverse is a place where no possibility is ever lost. Every flicker of potential, every path not taken, blossoms into its own complete universe. It is a cosmos of infinite stories, and you are the main character in an infinite number of them. 51. The anthropic principle. It's the ultimate cosmic survival bias. It's an answer to one of the most profound questions you can ask. Why is the universe so perfectly suited for us to exist? Think about the fundamental constants of nature. The strength of gravity, the charge of an electron, the expansion rate of the universe itself. Physicists have realized that if you were to tweak any of these values by even a razor-thin margin, the cosmos as we know it would be impossible. A slightly stronger nuclear force, and stars would burn out in 1,000,000 years. A slightly weaker one, and they never would have ignited at all. The universe is balanced on an impossibly fine knife's edge, and here we are. So, was it all designed for us? The anthropic principle offers a less direct, but perhaps more logical, answer. The writer Douglas Adams once imagined a puddle waking up one morning and thinking, "What a wonderful world I find myself in. An interesting hole I find myself in. Fits me rather neatly, doesn't it? In fact, it fits me staggeringly well. Must have been made to have me in it." Of course, the puddle is mistaken. The puddle exists precisely because it conforms to the shape of the hole. It couldn't be any other way. This is the core of the weak anthropic principle. We are that puddle. Our existence acts as a selection filter for the kind of universe we can observe. We are surprised to find the universe's constants are perfect for life, but we could not possibly have found ourselves in a universe where they weren't. You are here to ask the question only because you are in one of the rare universes where the conditions allowed for question askers to evolve. This idea becomes truly powerful when you pair it with the multiverse. If there are an infinite number of universes, each with its own randomly assigned set of physical laws, then it's not just possible, but statistically inevitable, that a few of them would have the right recipe for stars, planets, and consciousness. We didn't win a cosmic lottery against impossible odds. We are simply the natural outcome of a lottery with an infinite number of tickets. And all those other universes, the sterile and empty ones, have no one inside them to notice how unlucky they were. The fact that you are here to observe the universe isn't evidence that it was made for you. It's simply evidence that you are in the kind of universe where you could be made at all. 52. The fine-tuning problem. Imagine you're in a control room for the entire universe, standing before a console with dozens of dials. Each one is labeled the strength of gravity, the mass of an electron, the speed of light, the cosmological constant. These aren't just random numbers, they are the fundamental constants that write the rules for reality itself. And here's the unnerving part. For life, for stars, for any kind of complexity to exist, each of those dials must be set with breathtaking, almost unbelievable precision. If you were to nudge the dial for gravity just a tiny fraction, the consequences would be catastrophic. A little stronger, and the universe would have collapsed back on itself a split second after the Big Bang. A little weaker, and matter would have dispersed too quickly for stars and galaxies to ever form. No stars means no nuclear furnaces to forge carbon, oxygen, and the other heavy elements are made of. No you. And it's not just one dial. It's all of them working in concert. The value that governs the expansion of the universe, the cosmological constant, is fine-tuned to 1 part in 10 to the power of 100. That's a 1 with 120 zeros after it. To put that in perspective, getting that number right by chance is like throwing a dart from one end of the universe to the other and hitting a bullseye 1 millimeter wide. This is the fine-tuning problem. It's the observation that our universe seems to be balanced on a razor's edge for life. It's so wildly improbable that it feels less like a coincidence and more like a setup. It's like surviving a firing squad of 1,000,000 expert marksmen only to find that every single one of them missed. You wouldn't just shrug and say, "Gosh, I'm lucky." You'd immediately suspect there's a deeper explanation. So, what's the explanation for our cosmic luck? Some say it points to a designer who set the dials. Others believe there's some undiscovered theory of everything that proves these values had to be what they are. But there's a third, mind-bending possibility that fits perfectly in our journey down this iceberg. What if this isn't the only control room? What if there are countless other universes, a multiverse, each with a different set of random dial settings? In that vast cosmic lottery, most universes would be sterile, dark, and empty. But by sheer probability, a few like ours would happen to have the winning numbers. We find ourselves in a life-permitting universe for the simple reason that we couldn't exist anywhere else to ask the question. We didn't win the lottery. We just live in a universe where winning was possible. 53. MWI as a solution to fine-tuning. Why is our universe so perfect for us? It's a question that can feel almost theological. The fundamental constants of nature, the strength of gravity, the mass of an electron, the energy density of empty space, they all seem to be dialed in with breathtaking precision. If you were to tweak any of them, even by a minuscule amount, the whole cosmic show would collapse. Stars wouldn't ignite, complex atoms couldn't form, and you certainly wouldn't be here to ponder it. This is the fine-tuning problem. It's like walking up to a cosmic safe with a billion dials and finding it open on the very first try. It seems impossibly lucky. So, how do you explain this apparent miracle without invoking a divine fine-tuner? This is where the manyworlds interpretation offers a startlingly elegant, if vertigo-inducing, solution. MWI suggests that our universe isn't the only one. In fact, it posits that every quantum event splits reality into a near-infinite number of parallel branches. Now, apply that same logic not just to the spin of an electron, but to the fundamental constants of physics themselves. Imagine that in the fiery chaos of the Big Bang, all possible values for these constants were realized, each in its own separate, budding universe. In this vast, sprawling multiverse, the vast majority of universes are duds. They are sterile, chaotic, and lifeless. In one, gravity is so strong it immediately collapses back on itself. In another, the electromagnetic force is too weak for atoms to hold together. They are silent, dark, and utterly devoid of observers. But you are, by definition, an observer. Therefore, you can only exist in one of the universes where the conditions are right for observers to evolve. It's not that we won the cosmic lottery. It's that the multiverse prints every possible lottery ticket, and consciousness can only awaken to find itself holding a winning one. This idea is called the anthropic principle, but powered by the engine of the many-worlds interpretation. It elegantly reframes the question. Instead of asking, why is our universe so perfectly tuned for life? It forces us to ask, in which other kind of universe could we possibly have found ourselves? The answer, of course, is none. From this perspective, our existence isn't a miracle of luck, it's a statistical inevitability. Or, yes, consistent histories. Imagine your life isn't a single story, but a library of choose your own adventure books, all being written at the same time. Before you make a choice, the ink for every possible outcome is still wet, smudging together on the page. This is the core idea behind one of the most logical, yet deeply strange attempts to understand quantum reality. You know the basic quantum weirdness? A particle, like an electron, isn't in just one place. It exists as a cloud of probabilities. Only when you measure it does it seem to snap into a definite location. The consistent histories approach, developed by giants like Murray Gell-Mann and James Hartle, argues that asking, "Where was it before I looked?" is the wrong question. Instead, it asks, what are the possible stories kef of this electron? A history is just a sequence of events. Story A, the electron passed through the left slit and hit the top of a screen. Story B, it passed through the right slit and hit the bottom. The trick is, you can't just analyze any random set of stories. Think back to that wet ink. As long as history A and history B can interfere with each other, as long as their possibilities can overlap and create that quantum blur, you can't treat them as separate real narratives. They are part of one superimposed potential. But through a process called decoherence, the universe effectively dries the ink. The different paths stop interfering. They become distinct, separate, and non-contradictory. Only then do you have a consistent family of histories, a set of logical storylines about the universe to which you can finally assign probabilities. So how is this different from the manyworlds interpretation? It's a subtle but profound shift. Manyworlds boldly claims every single possible history branches off to become its own real parallel universe. Every page in that adventure book becomes a separate physical book on an infinite shelf. Consistent histories is more reserved. It provides the logical rules for which sets of stories are valid to even talk about. It says, here is a self-consistent framework of possibilities, but it doesn't necessarily demand that every unchosen path leads to another you. It suggests that reality isn't one definite movie playing out. Instead, the universe allows for a vast set of possible, logically coherent movies that could be played. The classical world you perceive, with its definite past and seemingly certain future, is just one of these consistent histories, plucked from an ocean of quantum potential, simply because it's a story that makes sense from beginning to end. And 5. Quantum eraser experiment. Imagine a detective at a crime scene with two possible entry points. By finding a single muddy footprint, he knows for a fact which door the culprit used. The mystery is solved. But what if, by simply taking his notebook with the footprint sketch and tossing it into a fire, he could retroactively force the culprit to have been a ghost, phasing through both doors at the exact same time? That is the logic-defying reality of the quantum eraser. It all builds on the famous double-slit experiment. You fire a single particle, like a photon, at a screen with two narrow slits. If you aren't looking, the photon doesn't choose a path. It behaves like a wave, spreading out and passing through both slits at once. On the detector screen behind, you see the evidence. A beautiful interference pattern of light and dark stripes, the signature of waves adding up and canceling out. But the moment you place a detector at the slits to peek to ask, which one did you go through? The wave-like magic shatters. The photon acts like a common bullet, picking one slit and the interference pattern vanishes, replaced by two simple clumps. Your knowledge forces reality to pick a side. The quantum eraser experiment is the ultimate cosmic cheat code. Scientists set up the experiment to gain that which path information, collapsing the wave and destroying the pattern. But here's the twist. They placed the final detector screen very far away. This gives them time. After the photon has already passed the slits and made its choice as a particle, but before it hits that final screen, they make another choice. To either keep the which path information, or to use a clever system of mirrors and beam splitters to effectively scramble and erase it, making it forever unknowable. And what happens is staggering. For the photons whose path information we keep, there is no interference. They remain particles. But for the photons whose path information we choose to erase, the interference pattern miraculously reappears. It's as if the photon, back in its past, gets a message from the future. A message that says, it's okay, they're going to erase the evidence. You can be a wave again. This delayed choice seems to shatter our concept of cause and effect. The many worlds interpretation provides a potential, though no less bizarre, escape hatch. It suggests you never changed the past at all. When the photon encountered the slits, the universe itself branched. In one universe, it went left. In a parallel universe, it went right. Your detector simply became entangled with these separate realities. When you choose to erase the information, you're not rewriting history. You are performing an action that realigns these branches from your perspective, allowing the wave functions from these different worlds to once again meet and interfere. You are simply choosing which sliver of the total, branching multiverse you get to perceive. Every act of knowing and forgetting is a decision about which reality is yours. Theory 6. Wheeler's delayed choice experiment. What if a choice you make right now could redefine what happened a moment ago? Not change it, but define it from an array of possibilities. This isn't philosophy, it's a real experiment that cuts to the very heart of what we call the past. You know the double slit experiment? Fire a single photon at a barrier with two slits. If you don't watch which slit it goes through, it behaves like a wave, passing through both at once and creating an interference pattern on the screen behind. But if you place a detector at the slits to see which path it takes, the magic vanishes. The photon acts like a simple particle, goes through one slit or the other, and the interference pattern disappears. Wave or particle? It all depends on whether you look. But here is where physicist John Wheeler introduced a mind-bending twist. He asked, what if you delay the choice? What if you decide whether to measure the path after the photon has already passed through the slits? Picture this. The photon is in flight. It has already navigated the two slits. It's now in the empty space between the slits and the final back wall. Only now, in this tiny fraction of a second, do you make your choice. You can either leave a photographic plate in place to see if an interference pattern builds up, the wave measurement, or at the last possible nanosecond, you can whip that plate away, revealing two detectors aimed back at the slits, which will tell you which path the photon came from, the particle measurement. The result is staggering. If you choose to look for the path, the photon is found to have gone through only one slit as a particle. If you choose to look for the interference pattern, the photon behaves as if it went through both as a wave. Your choice, made in the present, appears to have dictated the photon's past behavior. This doesn't mean you're a time traveler. It suggests something far stranger. It suggests the past is not a fixed, concrete story until it is observed. As Wheeler himself put it, the past has no existence except as it is recorded in the present. Your act of observation doesn't just reveal what happened, it participates in bringing what happened into being. The story of that photon's journey was unwritten until your measurement forced an ending, collapsing the quantum fog of possibilities into a single recorded fact within your universe. 57. Retrocausality, apparent. You know how the world works. You push a domino, and then it falls. The cause always comes before the effect. The past creates the present. But what if that's only half the story? What if the future could reach back and gently nudge the past into place? This is the core of retrocausality. Not time travel, not changing history, but the unsettling idea that an event in the future could be a cause for something that has already happened. It sounds impossible, like a movie playing in reverse. But in the strange world of quantum mechanics, the line between past and future begins to blur. Imagine you're writing a story. You decide on the ending first, a dramatic, unchangeable conclusion. Now, as you write the beginning and the middle, that ending looms over every word you type. It forces your characters to make certain choices, to be in specific places, to say certain things. The future of your story is actively shaping its past. In a way, the ending is causing the beginning. This is what some quantum experiments seem to hint at. In certain setups, the way we choose to measure a particle now appears to determine the path it took in the past. It's as if the particle knew what measurement you were going to make before you even decided. Did your future choice really send a message back in time? This is where the word apparent becomes so important, especially in the context of the many worlds. The theory suggests you didn't actually change a single fixed past. Instead, all possible paths for that particle existed simultaneously in a quantum fog of potential. Your measurement in the future didn't rewrite history, it simply selected which version of history is real for your branch of reality. You essentially pruned the tree of possibilities, making one path, one history, consistent with your present moment. The effect isn't the future changing the past, it's the present filtering it. So every decision you make, every observation, might be an act of solidifying one specific timeline from an infinite library of might have beens. It means your future isn't just a destination, it's a cosmic anchor, defining the very reality that led you to it. The story of your past isn't truly finished until your future is written. Stain? The problem of bare theory. What is a bare theory? Imagine your hand at the raw source code for reality itself. It's just pure, unadorned mathematics. No comments in the code, no user manual, just the equations that run the show. This is the heart of the bare theory problem, and it's one of the most sophisticated critiques leveled against the many worlds interpretation. The central engine of quantum mechanics, the Schrödinger equation, doesn't describe one single reality. It describes a sprawling, ever-branching tree of possibilities, the universal wave function. The many worlds interpretation takes a bold, minimalist stance. It says, this math, this equation, cis reality. There's nothing else. The theory is just the bare mathematics. But here's the disconnect. This is where the problem is for you. You don't experience a sprawling tree of possibilities. When you observe a quantum event, you don't perceive a ghostly smear of all potential outcomes. You get one, a single, definite result. Your life feels like a linear story, not an infinitely branching labyrinth. The bare theory describes the entire labyrinth, but it fails to explain why your consciousness seems to be on a single, well-defined path through it. It's like being given a blueprint for a mansion that shows 1,000 rooms, but offers no explanation for why you find yourself inside just one of them, completely unaware of the others. This leads to the thorniest issue of all, probability. If every single outcome of a quantum event actually happens in some branch, what does it even mean to say there's a 70% chance of an electron being found here, and a 30% chance of it being found there? Both outcomes occur with 100% certainty in their own newly formed universes. So, why do the numbers and the math so perfectly predict the frequency of results we see? Flip a quantum coin 1,000 times, and you'll find it landed on heads a number of times consistent with its probability. Why should that be the case if all outcomes are equally real? The bare theory itself doesn't give a satisfying answer. It just shows the branches. It doesn't explain why we should bet on one over the other. Critics argue that to solve this, proponents of many worlds have to add extra assumptions on top of the bare math complex arguments about logic and how a rational agent should behave. And in doing so, the beautiful simplicity of the math as the reality starts to look a lot less simple, revealing a deep chasm between the elegant world of the equation and the singular reality you are forced to experience. 59. The morality problem. This is where the floor gives way. If the many worlds interpretation is true, then for every decision you face, the universe splits. Every possible outcome happens. You take the job, and in another branch, you turn it down. You miss the bus, and another you catches it. You tell a lie, and another you tells the truth. So, what does it mean to make the right choice? At first, it seems to render morality meaningless. If you wrestle with a difficult decision and choose the noble path, you've only guaranteed that one version of you is noble. An exact copy of you, in a universe identical to this 1 moment ago, took the selfish path. The total amount of good and evil in the multiverse remains unchanged. It's a perfect conservation of sin and virtue. This can lead to a kind of cosmic paralysis. Why struggle to be good if a version of you is guaranteed to fail? Your best intentions are just one channel on an infinite television, and every other channel is also playing. But there's a far more profound and, frankly, terrifying way to look at it. Your choice isn't meaningless, it is the most meaningful thing imaginable. You aren't just deciding an outcome for yourself. You are deciding which universe gets to exist for your consciousness. Think of it like this. By choosing an action, you are casting a vote. You are throwing the entire weight of your existence behind one timeline over another. When you choose to be kind, you are not just performing a single act. You are birthing an entire branch of reality founded on that kindness. a universe where its positive consequences can ripple outward forever. And when you choose cruelty, you are doing the same. You are condemning a whole timeline to the consequences of that single selfish act. The many worlds theory doesn't absolve you of responsibility. It magnifies it to an infinite degree. The question is no longer just, what is the right thing to do? It becomes, which universe, out of all the possibilities, do I want to make real for myself? Every single moment you stand at the helm, not of a single life, but of an entire branching cosmos. And you have to choose which one you're willing to live in. Quantum immortality versus practical immortality. One is a ghost in the machine of the multiverse, a strange consequence of physics where you can't seem to die. The other is a dream of engineering, a future where we simply decide not to. Let's start with the quantum version. It's a direct, if bizarre, extension of the many-worlds theory. Imagine you're in a situation with a 50-50 chance of survival, a coin flip for your life. The moment that event happens, the universe splits. In one timeline, you perish. In the other, you live. The critical insight is this. Your consciousness, your continuous stream of awareness, can only experience the timeline where it continues to exist. It can't experience its own end. So, from your subjective point of view, you will always confine yourself in the branch where you survived. You watch the coin land on heads again and again for eternity. You're not invincible countless versions of, you have died in other worlds. But the you, that is, you, the one listening right now, only ever experiences the unbroken chain of survival. It's immortality by a cosmic loophole, a statistical inevitability of an infinite multiverse. Practical immortality is far more straightforward. It isn't a philosophical puzzle, it's an engineering challenge. This is the world of science fiction becoming science-backed. Think of it as defeating death on our own terms, within our one single timeline. It could be biological, using advanced gene editing and cellular regeneration to halt and reverse aging, making your body a self-repairing machine. Or it could be digital, where you upload your consciousness to a substrate that doesn't decay, living on as data in a vast network. This isn't about surviving a coin flip. It's about rebuilding the coin so it can never land on tails. It's an active, deliberate conquest of our biological limits. So, what's the core difference? Quantum immortality is passive. You do nothing. The universe, through its constant branching, simply filters out your extinction events from your personal experience. You are an eternal spectator to your own impossible luck. Practical immortality is active. It's humanity taking the controls, rewriting our source code, and building a future where the concept of a natural lifespan becomes a relic. One is a strange artifact of how reality might be structured. The other is a testament to what we want it to become. Which is the more profound idea? That you are already immortal, destined to live on as the sole survivor in an ever weirder world? Or that we might one day seize that power for ourselves and choose what forever looks like? 61. The cost of creating worlds. Every time a quantum event happens and a new branch of reality splits off, where does all that stuff come from? Where does the energy and matter for an entire new universe, a new you, originate? Doesn't this violate one of the most fundamental laws of physics? The conservation of energy? You can't just get a universe for free. This is one of the most common and intuitive objections to the many worlds interpretation. It feels deeply wrong, like a magician pulling an infinite number of rabbits from a hat. But the answer from many worlds is both simple and profoundly strange. There is no cost because nothing new is actually being created. Think of it like this. Imagine the universe isn't a single story, but an enormous, unread, choose-your-own-adventure book. All the pages, all the possible storylines are already printed and bound together. When you make a quantum choice, you aren't magically creating a new page with new ink. You are simply turning to a page that was already there, following one path while another version of you turns to a different page, following another. The universal wave function, in this view, contains all possible realities simultaneously. The split is just a process called decoherence, where these realities can no longer interact with each other. From your perspective inside one branch, it looks like a new world has been made. But from the outside, from the perspective of the multiverse itself, it's just the existing state of affairs unfolding. So, what about energy? The total energy of the entire multiverse remains constant. Each new branch inherits its slice of reality from the state that came before it. It's not a duplication, it's a division. Picture a single wide river of energy splitting into two smaller, parallel streams. The total amount of water flowing hasn't changed, it's just been partitioned into different channels. So, the real cost of creating worlds isn't paid in matter or energy, it's a cost paid by our intuition. We have to give up the comforting idea of a single, objective reality. The price is simplicity. We trade one world for an infinitely branching, unimaginably vast cosmos where every possibility is realized. The universe doesn't have to pay to create another you. Because from its perspective, all of you were already there. 6.2. Communication between worlds. If the many worlds interpretation is true, then for every choice you've ever made, a new universe branched into existence. A world where you took that other job, a world where you caught that train, a world where you never met the person you love most. They all exist. The ultimate question is, are they completely sealed off? Or could you somehow send a message across the cosmic divide? The primary obstacle is a phenomenon called quantum decoherence. Think of it like this. In the first instant of a choice, two new universes are like perfectly tuned radio stations broadcasting on the exact same frequency. But almost instantly, interactions with the environment. A stray photon, a single atom act as static. They knock each universe onto a slightly different frequency. The connection is lost. Our reality becomes sharp and singular because we are deaf to all other stations. So, how could we ever listen in? One dark theory suggests a form of one-way communication, quantum immortality. In any scenario where your death is a possibility, there's always a branch where, by some fluke, you survive. Your consciousness, the theory goes, would simply follow the path of survival. The message you receive from those other worlds is your own continued existence, a grim confirmation that countless versions of you just perished. A more direct approach might involve technology. Could a sufficiently advanced quantum computer act as a universal antenna? By manipulating quantum states in a perfectly isolated environment, perhaps it could detect the faint residual interference from a world that just split from our own. It wouldn't be a conversation. It would be more like finding a glitch in the matrix. A statistical anomaly in the data, a whisper of a probability that shouldn't be there. The ghost of a choice not taken. Proving this would be the single greatest discovery in history. It would confirm that you are not one but one of an infinite ensemble. What would you even ask another you? Did we make the right choice? Or what if he received a message first? A warning? A simple, terrifying hello? For now, the multiverse is silent. The barrier between worlds seems absolute. But silence doesn't mean no one is listening. It just means we haven't built the right radio yet. And in a reality infinitesimally close to your own, another you might be leaning in, right now, straining to hear the first crackle of static from a world they can't see, your world. The Deutsch-Wallace approach. It's the ingenious answer to the single biggest objection to the many worlds interpretation. If every possible outcome of a quantum event actually happens, what on earth do we mean by probability? Think about it. If quantum mechanics says an electron has a 70% chance of being here and a 30% chance of being over there, many worlds says the universe splits. In one universe, the electron is here. In another, it's there. Both are real. Both contain a version of you who just saw the result. So why do we, in our branch, feel the statistical pull of that 70%? If both outcomes are guaranteed to happen, the concept of probability seems to completely evaporate. Without a solid explanation for this, the many worlds idea isn't a scientific theory. It's just a wild story. It's a universe with no rules for what you should expect to see. This is the puzzle that physicists David Deutsch and, later, David Wallace dedicated themselves to solving. Their approach is a stunning piece of intellectual judo. They said, let's not add any extra magic or new rules to explain probability. Instead, let's prove that probability is an unavoidable consequence of the quantum rules we already have. when viewed through the lens of rational decision-making. Here's the core idea. Imagine you're an agent about to undergo a quantum split. You know the physics. You know the universe will branch, and there will be a UA who sees one result and a UB who sees the other. The quantum state tells you that branch A has a much larger mathematical weight or amplitude than branch B. Before the split, you have to place a bet on which experience you're going to have. What's the rational thing to do? Deutsch and Wallace demonstrated that the only logically consistent strategy is to bet in direct proportion to those quantum weights. To do anything else would be self-defeating. It's like knowing a coin is weighted 70-30 in favor of heads, but deciding to bet on tails anyway. It's an irrational choice. The very structure of the quantum formalism compels a rational agent to behave, as if the world is probabilistic. The probability isn't in some mysterious collapse. It's in the rational expectation of an observer living within the branching structure. So, probability isn't about counting worlds. It's about their measure. Think of it not as two separate paths, but as a river splitting. One channel is wide and carries 70% of the water, the other is narrow and carries 30%. You're a drop in that river, and you are overwhelmingly more likely to be found in the main channel. The Deutsch-Wallace approach argues that this measure of existence is what we perceive as probability. It transforms the many worlds interpretation from a philosophical curiosity into a rigorous, self-contained theory of reality, where the numbers that govern our world aren't just tacked on. They emerge from the very fabric of the multiverse itself. 64. The mindless laws of physics. Think of the most complex thing you can imagine. A swirling galaxy, the intricate network of a human brain, life itself. Now, imagine all of it was built by an instruction manual that has only one rule, repeated infinitely. Who this? No goal, no foresight, no intelligence. That's the unnerving and awe-inspiring idea behind the mindless laws of physics. The rules that govern our reality, gravity, electromagnetism, the nuclear forces, are, at their core, astonishingly simple. They are like the rules in a computer simulation, like Conway's Game of Life. You start with a few pixels on a screen and apply a handful of basic if-then statements. From these dead simple, unthinking instructions, you get patterns that move, evolve, and create structures so complex they look designed. They look alive. Our universe is the ultimate version of this. Gravity doesn't want to form a star, it's just a simple local rule that says mass attracts mass. But apply that mindless rule to a trillion particles over a billion years, and you get a sun. The complexity isn't in the law itself, it's an emergent property of that law being applied relentlessly and on a cosmic scale. And this process didn't stop with stars. It continued mindlessly until it built you. Every synapse firing in your brain right now, creating the very thought you're having about the sentence, is just chemistry and electricity following their programming. There's no ghost in the machine, no guiding hand, just mindless physical law cascading through time. This is where it connects profoundly to the many worlds. A mindless law doesn't make a choice. When a quantum particle is faced with the probability to be here or to be there, a mindful law might pick one. But a mindless law can't. It simply follows the math. And the math of quantum mechanics says the particle does both. It exists in all its possible states, and in the many worlds view, each of those possibilities branches off to create a new parallel universe. The laws aren't deciding your fate, they're generating every possible version of it. So, is there a grand design? According to this idea, no. There is only a grand computation. A simple, elegant algorithm running on the hardware of reality with no goal in mind. And the staggering, beautiful, terrifying complexity of everything we see, including our own consciousness, is just what happens when you leave it running for 8 billion years. The pilot wave theory. What if the quantum world isn't a game of chance at all? What if, beneath the haze of probability, reality is perfectly orderly, and every particle has known exactly where it's going since the dawn of time? This is the promise of one of the oldest and most controversial alternatives to mainstream quantum mechanics. Also known as Bohmian mechanics, this theory says that reality isn't made of fuzzy probability clouds. Instead, there are two things: real, solid particles and a real, physical pilot wave that guides them. Imagine you're a tiny speck of dust floating on the surface of a vast invisible ocean. You, the particle, have a definite, single location at all times. But your path is not your own. You are being steered by the complex, undulating surface of the pilot wave. This wave permeates all of space. It flows through everything, and its shape dictates the trajectory of every particle it touches. So, when you perform the famous double slit experiment, the electron doesn't magically go through both slits at once. It can't. It's a single point. It goes through either the left slit or the right one, period. But its pilot wave goes through both. The wave interferes with itself on the other side, creating an intricate pattern of peaks and troughs, like ripples in a pond. The particle, riding this wave, is then guided to land only in the areas where the wave is strongest, perfectly recreating the interference pattern we see, without any need for collapsing wave functions or splitting universes. In this view, there is only one you. There are no infinite other versions of yourself branching off into parallel worlds. There is just this one universe unfolding along a single predetermined path. The quantum randomness we think we observe is just an illusion, born from our ignorance of the particle's true starting position on its wave. But this beautiful simplicity comes at a strange price. Non-locality. The pilot wave is a single, unified entity across the entire cosmos. This means that a disturbance in the wave here could instantaneously change the guiding instructions for a particle on the other side of the galaxy. It's a universe connected by invisible, faster-than-light threads. A clockwork reality, yes, but one where every single tick is felt everywhere, all at once. Objective chance versus subjective uncertainty. Imagine you flip a coin, but you don't look. It's lying on the table, hidden under your hand. If I asked you the probability of it being heads, you'll say 50%. But that probability isn't a property of the coin anymore. The outcome is already a fact. It's either heads or it's tails. The 50% is a measure of your ignorance. This is subjective uncertainty. It's a gap in your knowledge about a world that is already settled. The answer exists, you just don't have access to it. It's like not knowing what's inside a wrapped gift. The gift is what it is. Your uncertainty is a state of your mind, not the gift itself. Objective chance is a far stranger beast. This is the idea that the universe itself is genuinely undecided, that before a quantum particle is measured, its state is not just unknown, it is literally unwritten. The cosmos hasn't made up its mind yet. According to this view, randomness isn't a bug in our knowledge, but a fundamental feature of reality. The universe truly plays dice. For a long time, this was the dominant way to think about the weirdness of the quantum world. But the many-worlds interpretation performs a breathtaking feat of intellectual judo. It completely eliminates objective chance. In this view, when a quantum measurement happens, the universe doesn't roll a die and randomly pick an outcome. It simply does everything. The world splits. In one branch of reality, a particle is measured as spin up. In another perfectly real branch, it's spin down. Both outcomes happen. So, where does our experience of probability come from? Why does it feel like a 50-50 shot? The theory pushes the problem back into the subjective realm, but in a way that's far more profound. Before the measurement, before the split, your uncertainty is no longer about what the universe will do. You can be 100% certain it will do both. Your uncertainty is about which of the resulting versions of you, this current stream of consciousness, will become. You know a descendant of yours will see heads and another will see tails. The probability is about your future location in the multiverse. You are about to fork and you have no knowledge of which path you will personally inhabit. The universe isn't random. Your journey through its infinite, branching corridors just feels that way. The Everett phone. It's a hypothetical device that could be the most profound or the most terrifying invention imaginable. It doesn't call the past or the future. It calls the present just, a different one. It calls another you. Named after Hugh Everett III, the father of the many-worlds interpretation, this thought experiment is designed to cut right to the heart of what branching realities would actually mean. Forget epic alternate histories for a moment. Think about the mundane. Think about the coin you flipped this morning. Heads, you wore the blue shirt. Tails, the gray one. According to manyworlds, both of those realities now exist, splitting off from the moment of decision. The Everett phone is the device that could, in theory, bridge that gap. Imagine it like an impossibly sensitive radio. You're tuned to your reality, your frequency. The phone allows you to dial the frequency that is infinitesimally different, the one where you wore the gray shirt. You pick up the phone, you dial your own number. And on the other end, a version of you, identical in every way except for their wardrobe, answers. What do you even say? Why, me. How's the gray shirt? It seems trivial, but now let's up the stakes. Imagine you're part of a quantum experiment, a real-life Schrödinger's cat scenario. A particle's spin is measured. If it's spin up, you live. If it's spin down, a poison is released and you die. The measurement is made. You open your eyes, you're alive. The particle was spin up. Relieved, you reach for the Everett phone. You dial the number for the branch where the particle was spin down. What do you hear? Do you hear the sound of your own death? Do you hear the phone ringing unanswered in an empty room? Or worse, does a grieving partner or family member pick up, their voice trembling as they ask who's calling? This is the true purpose of the Everett phone thought experiment. It's not about the technology, it's about the devastating emotional and philosophical consequences. It forces you to confront the idea that for every success, there's a version of you who failed. For every lucky break, there's a you who wasn't so lucky. The phone wouldn't just be a communication device, it would be a direct line to your own ghosts, a constant, chilling reminder of all the other lives you are living, and all the deaths you are dying across the multiverse. 68. Quantum mechanics of black holes. For a long time, we saw a black hole as a simple brute. A cosmic dead end. A point of no return governed by the smooth, elegant laws of Einstein's gravity. But when you zoom in, right to the edge of forever, that classical picture shatters. You find a place where the fabric of spacetime itself begins to fizz with quantum uncertainty. This is where our two great pillars of physics collide. General relativity, the master of the large and the heavy, and quantum mechanics, the master of the small and the strange. At a black hole's event horizon, they go to war. Relativity says it's a smooth, unremarkable boundary. You could float past it without even noticing until it's too late. But quantum mechanics insists that no place in the universe can be that simple, that even the vacuum of space is a roiling sea of activity. Imagine this quantum sea is filled with pairs of virtual particles, a particle and its antiparticle, constantly popping into existence and annihilating each other in a flash. It's happening everywhere, all the time, even in the empty space right in front of you. But right at the edge of a black hole, a pair can be separated. One particle might fall in, while its partner escapes. The black hole's immense gravity gives that escaping particle the energy to become real. This steady trickle of escaping particles is Hawking radiation. It means the black hole isn't truly black. It glows incredibly faintly, and over unimaginable timescales, it evaporates. It loses mass, shrinking until it vanishes completely. But this evaporation creates a profound paradox. A core law of quantum physics is that information can never be destroyed. The unique blueprint for a star, a planet, or anything that falls into a black hole can be scrambled, but it can't be erased from the universe. Yet, a black hole seems to do just that. It swallows information, and the Hawking radiation that leaks out appears to be random thermal noise with no memory of what fell in. So, when the black hole is finally gone, where did the information go? Did the universe just break its own most fundamental rule? This is the information paradox, and it forces us to question reality itself. Is the information somehow encoded on the surface of the black hole, like a cosmic hologram? We don't know. A black hole, then, is more than an object. It's a message, a boundary where our understanding ends and where the clues to a new unified theory of quantum gravity are waiting. 6.9. The black hole information paradox. This is what happens when an unstoppable force meets an immovable object, but for the laws of physics themselves. It's one of the deepest puzzles in science, a direct conflict between the two pillars of our modern understanding of the universe. On one side, you have Einstein's theory of general relativity. This is the theory of the big and the heavy. It tells us that when something falls into a black hole, it passes the event horizon and is lost forever. The black hole itself can be described by just three numbers: its mass, its spin, and its charge. So, if you throw an encyclopedia into a black hole, and then throw a pile of rocks with the same mass, the final black hole is identical. All of the intricate information that made up the encyclopedia, the words, the ideas, the history, is seemingly wiped from existence. But on the other side, you have the immovable object, quantum mechanics. This is the theory of the small, and one of its most fundamental, unbreakable laws is that information can never be truly destroyed. You can burn a book, but if you could track every single particle of ash, smoke, and heat, you could theoretically piece the book back together. The information is just scrambled, not erased. The universe, according to quantum mechanics, keeps a perfect record of everything. So you have a cosmic standoff. Relativity says the information inside a black hole is gone. Quantum mechanics says that's impossible. And then, Stephen Hawking made the problem even worse. He discovered that black holes aren't completely black. They slowly leak energy, called Hawking radiation, and over immense timescales they evaporate and disappear completely. The problem is, his original calculations showed this radiation was random, carrying no information about what fell in. So, when the black hole is gone, where did the encyclopedia's information go? It can't be inside the now non-existent black hole, and it didn't seem to get out. This paradox has forced physicists to question their most basic assumptions. The leading idea today is a concept called the holographic principle. It suggests that the information isn't lost inside the black hole at all. Instead, it's encoded on the two-dimensional surface of the event horizon, like a cosmic hologram. As the black hole evaporates, this information is slowly and intricately imprinted onto the outgoing Hawking radiation, returning it to the universe in a profoundly scrambled form. Solving this isn't just an academic exercise. It's a direct path toward a theory of everything that finally unites gravity with the quantum world. 70. MWI and the information paradox. One of the most sacred, unbreakable laws in physics is that information can never be destroyed. It can be scrambled, hidden, or rearranged, but it can never truly be erased from existence. Think of it like a cosmic book where you can't burn the pages. But then, we have black holes, the universe's ultimate shredders. When something falls past the event horizon, it seems to be gone forever. And worse, Stephen Hawking discovered that black holes aren't truly black, they slowly evaporate, leaking a faint glow known as Hawking radiation. The problem is, this radiation appears to be completely random, a thermal hiss containing none of the intricate information that fell in. The book, it seems, has been turned to ash. The law is broken. This is the information paradox, a deep contradiction between quantum mechanics and general relativity. So, where does all that precious information go? This is where the manyworlds interpretation, or MWI, offers a truly mind-bending escape clause. What if the black hole isn't a shredder, but a doorway? In the MWI framework, a black hole doesn't destroy information, it broadcasts it to other universes. Imagine information is a river flowing with purpose. A black hole is like a colossal prism placed in its path. From our side, it looks like the river simply vanishes into the prism. The Hawking radiation we see is like a faint, featureless glow leaking from its surface. But MWI suggests that on the other side of the prism, that single river of information has been split into an infinite number of new rivers, each flowing into a separate, parallel world. The information isn't lost, it's just not into our universe anymore. Every particle, every quantum state that ever fell into that black hole is perfectly preserved, just shunted sideways across the multiverse. The black hole, then, is not an endpoint, it's a branching point. It's the universe's way of upholding its most sacred law, even if it has to create countless new realities to do it. The story of what fell in is never erased. It's just being told in a library with an infinite number of rooms, and we are only standing in one. 71. The cosmological constant problem. It's often called the worst prediction in the history of physics. Imagine you tried to calculate the height of a small child, and your answer was the diameter of the entire Milky Way galaxy. That is the scale of the error we're talking about. It's a chasm in our understanding so deep, it suggests we're missing something truly fundamental about reality itself. Here's the breakdown. On one hand, you have Einstein's theory of general relativity. It allows for a kind of energy of space itself, a cosmological constant that pushes the universe apart. When astronomers looked out at distant galaxies, they discovered that the universe's expansion is indeed accelerating, driven by this mysterious force we now call dark energy. But the measured amount of this energy is exquisitely, incomprehensibly tiny. It's barely there at all. On the other hand, you have quantum field theory, our best description of the subatomic world. According to quantum mechanics, empty space isn't empty. It's a roiling, bubbling soup of virtual particles constantly popping in and out of existence. This vacuum energy should, in theory, be the source of that cosmological constant. So, physicists tried to calculate its value, and the number they got was monstrous. It was 120 orders of magnitude larger than what we actually observe. That's a 1 followed by 120 zeros. This isn't a small rounding error. It's like predicting your bank account should contain all the money on planet Earth, but when you check the balance, you find you only have a single dollar. The discrepancy is so profound it tells us that our two-pillar theories of the universe, relativity and quantum mechanics, are violently disagreeing about the very nature of nothingness. So, what's the solution? One of the most tantalizing possibilities takes us right back to the theme of this journey, the multiverse. What if this isn't a calculation error but a selection effect? Perhaps there are countless universes, an infinite cosmic foam, and in each one, the cosmological constant has a different random value. In the vast majority of them, the value is huge, causing them to either instantly collapse or rip themselves apart before a single atom could form. We, by definition, could only find ourselves in a universe where the value was fine-tuned to be incredibly small, allowing galaxies, stars, and ultimately, you, to emerge. Our universe isn't special because it was designed, it's special simply because we're here to see it. This catastrophic failure of a prediction might just be the strongest clue we have that our reality is just one habitable island in an infinite and mostly lifeless cosmic ocean. MWI and the cosmological constant. This is where we confront what's been called the single worst prediction in the history of physics. Imagine you calculate the weight of a single grain of sand, and your theory predicts it should weigh as much as the entire Milky Way galaxy. That's the scale of the problem we're talking about. The cosmological constant is the energy of empty space itself, a subtle, background push that's accelerating the expansion of our universe. Our best theories, based on quantum mechanics, predict this energy should be colossal, a value so large it would have ripped the universe apart moments after the Big Bang. Yet, when we measure it, we find a value that is shockingly, exquisitely small. It's about 120 orders of magnitude smaller than the prediction. It's not zero, but it's so close that it feels like a cosmic joke. So how could the many-worlds interpretation possibly help? It offers a radical perspective shift. What if the cosmological constant isn't a single, fundamental number? What if, in the vast, branching tapestry of the multiverse, every possible value for this constant exists in some world? Think of it like a cosmic lottery. In almost every single universe, the ticket is a loser. The cosmological constant is huge, and that universe either blows apart instantly or collapses in a flash. No stars, no galaxies, no life. It's just cosmic static. But with a near infinite number of universes playing, it's statistically inevitable that a few winning tickets will be drawn universes where the constant is a tiny life-permitting value. And, of course, where do you think you find yourself? You can only find yourself in one of the winning universes. This is the anthropic principle at its most powerful. We can only observe a universe that is compatible with our own existence. It's not that the universe was fine-tuned for us. It's that we could only have evolved in a branch of the multiverse that, by sheer chance, happened to be fine-tuned. So, the reason the energy of space seems so perfectly balanced for our existence isn't a miracle. It's a selection effect. You are living in one of the rare quiet corners of the multiverse where the cosmic storm is calm enough for something like you to wake up and wonder about it all. The other worlds, the vast majority, are silent, violent, and utterly empty. Eternal inflation. What if the Big Bang wasn't a singular event? What if it was just one pop in an endless cosmic film of creation, a process that is still happening right now and will never ever stop? This is the staggering idea behind eternal inflation. To understand it, you have to think of the energy that powered our own Big Bang, a mysterious force field called the inflaton field. The theory of inflation says this field drove a period of hyperexpansion in the first fraction of a second of our universe's existence. Eternal inflation takes this one crucial step further. It suggests that this expansion, on the largest of scales, never actually ended. The engine of creation is still running. Imagine space-time as a gigantic ocean, bubbling with energy. This is the inflaton field. Most of this ocean is expanding at a blistering, incomprehensible rate, stretching space-time faster than the speed of light. But, like water boiling in a pot, random pockets of this ocean can suddenly cool down. In these pockets, the rapid inflation stops, the energy is released, and a universe like ours is born, a bubble of calm in a raging sea. Our entire observable universe, with all its galaxies and stars, is just one of these bubbles. And here's the mind-bending part. While our bubble has settled down, the vast ocean of space-time outside our bubble is still inflating exponentially. As it expands, it's constantly creating new pockets, new bubbles, new universes, each with potentially different physical laws, different constants, a completely different reality. This isn't just a philosophical fancy. For many physicists, it's a direct prediction of the inflationary model. It transforms the multiverse from a possibility into an inevitability. It creates a fractal-like structure of reality where universes are eternally budding off from one another. So, when you look up at the night sky, you're seeing a tiny corner of one bubble. Beyond the horizon of what you can see, the cosmic ocean continues to churn, giving birth to an infinite number of other worlds. And in an infinite number of worlds, every possibility is played out, including infinite versions of you, living out lives you can't even imagine, all born from a process that has no end. 79. The arrow of time. Why can you remember what you ate for breakfast, but not what you'll have for dinner tomorrow? Why does a glass shatter into 1,000 pieces, but 1,000 pieces never leap off the floor to reassemble into a glass? This one-way street we call time feels deeply intuitive, yet it's one of the biggest mysteries in physics. Here's the puzzle. At the most fundamental level, the laws that govern reality don't care about direction. A video of a planet orbiting a star looks perfectly normal if you play it in reverse. The equations of gravity and electromagnetism work just as well backwards as they do forwards. So if the basic rules are reversible, why is your life so stubbornly irreversible? The answer has to do with a concept called entropy. It's a measure of disorder. And the second law of thermodynamics states that in a closed system, disorder always increases. Imagine a pristine, unshuffled deck of cards all arranged by suit and number. This is a state of low entropy. It's highly ordered. Now, throw them in the air. When they land, they'll be a random, disordered mess. This is high entropy. You could throw them 1,000,000 more times, and they will never, ever land back in their original perfect order. The universe works the same way. It always moves from order to disorder. Your hot coffee cools down, spreading its heat into the room. It never spontaneously gathers heat from the room to become hot again. The arrow of time is simply the universe obeying this law. It all began with the Big Bang, an event of impossibly perfect order, a state of incredibly low entropy. Ever since that moment, the universe has been expanding, cooling, and shuffling itself into a more disordered state. Time's arrow is the aftershock of that initial creation, the long, slow process of the cosmic deck of cards being shuffled. In the context of manyworlds, this takes on another beautiful dimension. Every quantum event, every split into new timelines is an irreversible step. The multiverse can't unsplit. The number of worlds always increases, never decreases. The past is the single trunk of the tree of reality you came from. The future is the infinite, ever-expanding canopy of branches ahead. You experience the arrow of time because you are riding one of these branches as it grows, moving inexorably away from the simple trunk and into the chaotic, complex, and unknowable future. 75. String theory landscape. This is the idea that our universe isn't a singular, destined creation, but just one habitable valley in a vast, almost infinite cosmic terrain of possibilities. To understand this, you have to start with string theory's biggest prediction, that there are more dimensions than the ones you see. To account for our reality, these extra dimensions are thought to be curled up, compacted into incredibly tiny, complex shapes, far too small for us to ever perceive directly. The problem, or perhaps the beauty, is that there isn't just one way for these dimensions to curl up. There are a staggering number of possibilities. The most common estimate is 10 to the power of 500. That's a 1 followed by 500 zeros. A number so colossally large that if every single atom in our observable universe had its own universe, you wouldn't even be close to scratching the surface. Now, picture this entire collection of possibilities as a true landscape. It has soaring, jagged peaks and deep, tranquil valleys. Each and every point on this landscape represents a potential universe with its own unique set of physical laws, its own cosmic DNA. The peaks represent unstable, chaotic realities that would flash in and out of existence, unable to sustain themselves. But the valleys are different. They are stable. They are pockets where the laws of physics are just right, allowing a universe to form and endure for billions of years. Our universe, the one you're in right now, is just one of those valleys. We happen to live in a vacuum state where the strength of gravity, the charge of an electron, and the speed of light are precisely what they are. It's a universe that allows for stars, planets, and, ultimately, you. But the landscape suggests we are not alone. The theory allows for countless other valleys, each potentially giving birth to its own bubble universe in the inflationary chaos following the Big Bang. This implies a multiverse not of simple copies, but of infinite variations. Universes where fundamental constants are slightly different. Universes with entirely different particles and forces. And in a collection with 10 to the power of 500 options, the anthropic principle kicks in. Of course, you find yourself in a universe that can support your existence. But it also means that across that unfathomable landscape, other valleys might exist that are virtually identical to ours. Other pockets of reality where another version of your consciousness is looking up at the stars, wondering if they're alone. A cosmic echo in a neighboring valley of the landscape. 76. Theory. It's the whispered secret at the heart of modern physics. A candidate for the final theory, the theory of everything. The M itself is a mystery. Some say it stands for magic, mystery, or membrane. But its true name is known only to its creator. At its core, M-theory is an attempt to read the source code of the universe. Before M-theory, the world of physics was fractured. There wasn't one string theory, there were 5s. 5 competing sets of equations, each describing a universe of tiny vibrating strings. They all worked mathematically, but they described different realities. Which one was ours? It was a beautiful, chaotic puzzle with too many pieces. Then, in 1995, a physicist named Edward Witten stood up and proposed a breathtaking idea. He suggested that these 5 theories weren't competing at all. They were just different glimpses of something far grander. Imagine you're in a dark room with a complex, multifaceted crystal. You shine a flashlight on it from 5 different angles. Each angle projects a different 2-dimensional shadow on the wall. You might think you're seeing 5 different objects, but in reality, you're just seeing 5 perspectives of one single higher dimensional truth. The 5 string theories were the shadows. M theory was the crystal, existing in a staggering 11 dimensions. And this is where the picture of reality truly shatters. M theory isn't just about one-dimensional strings. It introduces brains, vast, multi-dimensional membranes. A string is a 1-brain. A sheet of paper is like a 2-brain. And our entire universe, everything you've ever known, every star, every galaxy, you might exist on a giant 3-brain, a 3-dimensional island floating in a higher dimensional sea. And you are not alone in this sea. M theory allows for other brains, other universes, to exist parallel to our own. They could be floating just a millimeter away from you right now, but in a direction you can't point to, an 11th dimension you can't perceive. These brain worlds could have different laws of physics, different histories. And on some of them, another version of you might be listening to a different story, living on a different page in the grand cosmic book. The theory even suggests that the Big Bang itself could have been caused by the cataclysmic collision of two of these cosmic membranes, a clash of worlds that gave birth to our own. 77. Brain cosmology. The universe you perceive. Every galaxy, every planet, your very consciousness might exist on a vast three-dimensional membrane, a brains for short. Imagine our reality is just one slice of bread in an infinite cosmic loaf. This loaf, the higher dimensional space it sits in, is called the bulk. And floating within this bulk, perhaps parallel to our own, are other slices, other universes. We are living inside one of these membranes, completely unable to see or touch the others that might be hovering right next to us. This isn't just a wild guess. It offers a beautiful solution to one of physics' biggest puzzles. Why is gravity so incredibly weak? Compared to electromagnetism, it's like a whisper next to a thunderclap. Brain cosmology suggests an answer. While forces like light and matter are stuck to our brain, like ink on a page, gravity is different. Gravity is the one force that can leak off our brain and travel through the bulk. The gravity you feel is just a fraction of its true strength, the faint echo of a force that permeates all dimensions. It's diluted because it has to fill a space far larger than our mere 3 dimensions. And the Big Bang? In this model, it wasn't a singular point of origin from nothing. Instead, it might have been an unimaginably violent event, the collision of two parallel brains. Picture two colossal sheets smacking together in hyperspace. That cosmic clap is what we perceive as the birth of our universe. It's energy converting into the matter and radiation we see today. Our beginning wasn't a creation, but a cosmic impact. This leads to a staggering implication, bringing us back to the question of infinite use. If our universe is just one brain among many, then countless other worlds could be floating just out of reach. They aren't light years away across space. They could be less than a millimeter from you right now, separated only by a dimension we cannot perceive. Each brain could have wildly different laws of physics, or it could be a near-perfect duplicate of our own. On one of those brains, another version of you might be lying awake, wondering if another you exists on a parallel slice of reality, just a quantum leap away. Our entire cosmos, a fragile film in an infinitely larger hyperspace, completely unaware of the other worlds drifting silently just next door. 78. The holographic principle. This is the radical, almost unbelievable idea that our three-dimensional reality is an illusion. That you, the room you're in, the stars in the night sky, everything you perceive as solid and real is nothing more than a complex projection. A hologram, written on a distant two-dimensional surface that marks the very edge of our universe. This isn't just science fiction. It emerged from the mind-bending physics of black holes. Physicists like Jacob Bekenstein and Stephen Hawking discovered something deeply strange. The amount of information a black hole can hold isn't determined by its three-dimensional volume, but by its two-dimensional surface area. It's as if everything that ever fell inside is somehow encoded on the boundary, the event horizon. This was a profound clue. If information in the densest objects in the cosmos lives on a surface, could the same be true for the entire universe? Think of the hologram on your credit card. It's a flat 2D sticker, but when light hits it just right, it projects a three-dimensional image. The holographic principle suggests our universe works the same way, but on a cosmic scale. The sticker is the boundary of our observable universe, and we are the 3D image projected from it. Every particle, every interaction, every thought you've ever had could be a manifestation of pure information bits and bytes etched onto that cosmic horizon. It suggests that information is the true fundamental reality, and the space and time we experience are emergent properties of that code. So, what are you? According to this principle, you aren't just a collection of atoms moving through 3D space. You are a holographic projection. Your consciousness, your memories, your very sense of self, all of it is a complex pattern of information being read from a 2D cosmic hard drive. It means the universe might not be a place full of things, but a process that is calculating itself into existence. And you are a part of that breathtaking cosmic calculation, a beautiful illusion unfolding from a simpler, flatter reality we can never touch. 79. The problem of evil in MWI. You know the classic theological question: If there is an all-powerful, all-knowing, and all-good God, why does suffering exist? The many worlds interpretation doesn't answer this question. Instead, it takes the problem, straps it to a rocket, and launches it into an abyss of infinite horror. In the classical view, a tragedy is a single terrible event. A car swerves at the last second, and you're safe. A terrible diagnosis turns out to be a false alarm. In these moments, you might feel lucky or blessed. But in the many worlds framework, luck doesn't exist. There is no dodging the bullet. There is only the branching of reality. For every timeline where you swerve and survive, there is another, equally real timeline where you don't. For every world where your loved one makes a full recovery, another branch is created where they suffer and die. Every single thing that can happen does happen across the multiverse. Let that sink in. This isn't a metaphor. According to this theory, there is a version of you, right now, experiencing the worst possible fate you can imagine, and another version of you experiencing a fate that's slightly less terrible, and another, for every conceivable permutation of suffering. It reframes the problem of evil entirely. The issue is no longer that a benevolent God allows suffering to happen. The issue is that he designed a system where every possible suffering is guaranteed to happen. Think of reality as a book. The classical problem of evil is like asking why the author wrote such a tragic chapter. The many worlds problem of evil is discovering the author didn't just write one tragic chapter. He wrote every possible chapter, from the most beautiful to the most depraved, and bound them all together, declaring every single one of them to be true. Your personal consciousness is just reading one page. You might be on a happy page, and for that, you can be grateful. But you are intrinsically linked to the infinite other yous who are on the pages of agony. Their suffering isn't a distant possibility, it's a physical reality in a parallel space. The question is no longer, why is there evil in the world? It becomes, why was a multiverse created where the total sum of suffering is, by definition, infinite? The doppelganger, you. This isn't the mythical creature from folklore, the ghostly omen of bad luck. This is a conclusion of cold, hard physics, a statistical certainty. Somewhere in the unfathomable darkness of space, in a region so far away you could never hope to see it, there is another you, a person made of the exact same arrangement of atoms, living on a planet identical to Earth, at this very moment wondering, what's out there? How is this possible? Think of it like a cosmic deck of cards. Our observable universe, everything we can see, is a finite space. It's unimaginably vast, but it's not infinite. And within this space, there are only a finite number of ways particles can be arranged to form stars, planets, and people. The number is staggering, a 1 followed by 10 to the power of 122 by some estimates. But it is finite. Now, if the greater universe beyond our horizon is truly infinite, then it's just a matter of probability. An infinite space with a finite number of arrangements means that every single possible arrangement must repeat. And not just once, but an infinite number of times. Cosmologists call our pocket of the universe a Hubble volume. It's our cosmic bubble. And if space stretches on forever, then there are infinite other bubbles out there, each a unique shuffle of the cosmic deck. In one of those distant bubbles, the particles aligned in the exact same way they did here. The result is your perfect twin, your doppelganger, who has lived your exact life up to this second, now listening to these exact words. But the implications are even stranger. A little further away is a you who chose a different path this morning. A you who pursued that career you only dreamed of. A you who said yes instead of no at a critical moment in your life. Every possible version of your existence, every choice you could have made, is being lived out by a physical copy of you in some far-flung corner of reality. You can never meet them. The sheer distance ensures you are forever causally disconnected, like characters in separate novels that can never cross pages. Your uniqueness, then, isn't in your physical form, but in your singular conscious experience of this particular arrangement. You are the sole audience to this specific life. And as you exist in this moment, consider this. Across the endless cosmic ocean, another you is also here, living out a slightly different version of today, one of an infinite number of stories, all starring you. 1. Quantum Darwinism. Failure modes. Imagine our shared reality is a radio broadcast. Quantum Darwinism is the process that ensures we are all tuned to the same crystal clear channel, all hearing the same song. It's the universe's way of taking a fuzzy quantum maybe and making it a definite classical yes by imprinting countless copies of that yes onto the environment. It's survival of the fittest information. You and I agree that a tree is a tree because the information of that tree has successfully and redundantly published itself everywhere. But a failure mode is what happens when that broadcast signal corrupts. It's a crack in the very foundation of objective reality. The first failure mode is insufficient redundancy. Think of the universe as a cosmic photocopier. For us to agree on an outcome, it needs to make millions of perfect copies. But what if it only makes one or two blurry, faint ones? In this scenario, different observers could interact with the same system and genuinely, legitimately measure different things. Not because they branched into different worlds, but because the single world they share failed to produce a coherent fact for them to agree upon. Your reality and my reality would diverge, even as we stand side by side. Another failure mode is a corrupted environment. The information gets copied out, but the environment itself is too noisy, too chaotic to hold it. It's like trying to write a message on a piece of paper that's already covered in random scribbles. The message is there, but it's completely lost in the static. In such a universe, objective facts could never form. The quantum possibilities would never collapse into a single, stable story. Reality would be a constant, unreadable hiss. Finally, there's the most unsettling possibility: observer malfunction. What if the broadcast is perfect, the information is redundant and clear, but our radios are broken? What if our own consciousness, our very method of measurement, is incapable of properly decoding the information from the environment? We might perceive a reality, but it would be a distorted, private hallucination. We think we are all tuned to the same channel, but we are each hearing a warped song of our own making. These failure modes suggest a universe far stranger than a simple multiverse. They suggest a universe that could, at any moment, fail to be a universe at all. D2. The quantum Zeno effect. It's the quantum mechanical proof of the old saying, a watched pot never boils. Except in this case, it's not just a saying. It's a demonstrable, almost magical, feature of our reality. Imagine a single, unstable, radioactive atom. Left to its own devices, it exists in a ghostly state of superposition, a blend of both its original form and its decayed form. Over time, the probability of it having decayed increases. But what happens if you decide to watch it? Not just a glance, but a relentless, continuous observation. Let's say you measure the atom every nanosecond to see if it has decayed. The first time you look, you find it hasn't. The very act of your measurement forces the atom to choose a definite state. By observing it as intact, you have essentially collapsed its wave function and reset its evolutionary clock back to zero. The probability of it decaying starts all over again. A nanosecond later, you look again. Still intact? The clock is reset. Again. And again. By bombarding the atom with rapid, successive measurements, you never give its probability of decay a chance to grow. You are pinning it to its initial state, effectively freezing it in time. The pot never boils because you never stop looking at it. This is more than just a neat trick. It's a profound statement about the relationship between consciousness and reality. Think of it like a spinning coin, balanced perfectly on its edge. It's destined to fall to heads or tails. But if you could gently tap its edge 1,000 times a second, you could keep it spinning indefinitely, preventing it from ever decaying into a final state. That's what you're doing to the atom with your observation. And in the context of the many worlds, this becomes even stranger. Every time you measure the atom and find it hasn't decayed, the universe branches. In another world, it did decay and a version of you witnessed it. But you, the observer who keeps looking, are actively selecting the timeline where it remains stable. You are steering your consciousness down a very specific, improbable path through the multiverse. The path where nothing ever changes simply because you refuse to look away. 3. The nature of self. You feel it, don't you? That constant, unshakable sense of being me. The pilot in the cockpit of your mind. The one listening to my voice right now. But what is it really? If you had to point to this self, where would your finger land? You might point to your body, your brain, but this vessel is in a constant state of flux. Every 7 to 10 years, almost every atom that makes you is replaced by a new one. You are, quite literally, not made of the same physical stuff you were as a child. Think of the ship of Theseus, a vessel whose planks are replaced one by one until no original timber remains. Is it still the same ship? Are you still the same you? Perhaps, then, the self isn't in our atoms, but in our minds. In the continuous ribbon of our memories, our personality, the story we tell ourselves about who we are, but this is also a fragile foundation. Memories can be false, they can fade. Personalities can be altered by experience or injury. If you woke up tomorrow with total amnesia, would the you from yesterday be gone forever? Is the self just a story, a delicate thread of consciousness we desperately try to keep from snapping? There's a more radical idea that there is no core self at all. Philosophers call it the bundle theory, the idea that you are not a single entity having experiences, but rather a flowing bundle of perceptions, thoughts, and feelings. There's no permanent you experiencing the world, you are the experience. Imagine yourself not as a solid statue, but as a river. It's always moving, always changing, yet we give the entire process a single name. You are not a thing, but a process. And this is where the self shatters across the multiverse. If you are a process, a river of moments, then every quantum choice is a fork in that river, a point where your story branches. The version of you listening to this is just one timeline. In another, you turned right instead of left this morning. In another, you never found this video. Each branch is a valid continuation of the consciousness that was you a moment ago. The self isn't a single point traveling through time. It's an ever-expanding tree of possibilities, an identity fractured across countless realities. The I you feel so certain of is just one leaf on an infinite tree. The Av, consciousness and branching. If the universe splits, where do you go? This is the single most haunting question in the many worlds interpretation. It's where physics crashes into the deepest sense of self. The theory suggests that at every quantum event, reality branches into multiple parallel streams. A particle is measured to be spin up here and spin down in a newly created, equally real universe. But you are not a single particle. You are a 70 octillion atom observer. What happens to your consciousness during a split? The key insight is that you don't watch the branching happen from the outside. You are part of the branching. Your brain, the very act of you observing the world, is a complex quantum system. When you look at a quantum experiment, the information from that particle interacts with the photons hitting your retina, which triggers a cascade of neural firings. That entire chain from particle to your conscious thought is the branching event. Think of your consciousness not as a driver choosing a road, but as a passenger on a train. Up ahead, the track forks. A quantum event is the switch. The train car you're in, your entire physical reality, is shunted onto one of the tracks. In that instant, an identical train car with an identical you inside is shunted onto the other. From your perspective, nothing happened. The journey just continued. You feel a perfect, unbroken stream of awareness. You remember the track before the fork, and you experience the track after. You have absolutely no knowledge of that other train, that other you, now speeding away into a different future, convinced they are the one and only you. This means your consciousness doesn't cause the split. It undergoes the split. The you that decided to listen to this and the you that clicked on a different video both exist. They share an identical past right up until the moment of that decision. After that, their experiences diverge. Each version of you is equally real, and each is utterly convinced of their own unique existence, carrying a perfectly consistent set of memories that justifies the world they see around them. There is no original you. There is only the you on this branch listening to these words, completely unaware of the countless others. Ordered, the sum over history's formulation. How does a single particle, like an electron, get from point A to point B? The classical answer is simple. It follows a single, predictable path like a tiny bullet. But quantum mechanics has a far more profound and unsettling answer. It suggests the particle doesn't choose a path. It takes all of them. This is the brilliant, almost fantastical idea from physicist Richard Feynman. He asked us to imagine that to get from here to there, an electron explores every conceivable route simultaneously. Not just the straight line, but the wiggly one, the one that loops around, the one that zips out to the edge of the galaxy and back in an instant. Every single possible history that connects the start and end point happens. Think of it like a cosmic democracy of paths. Each potential journey gets a vote, but not all votes are equal. Feynman developed a mathematical way to assign a value to each path, a kind of complex number we can picture as a tiny spinning arrow. The magic happens when you add up, or sum, the arrows from all these infinite histories. Here's the key. For paths that are very similar to each other, the ones clustered around the straight, efficient route, their little arrows end up pointing in roughly the same direction. When you add them together, they reinforce each other, creating a huge, powerful arrow pointing towards a specific outcome. This is the path of classical physics, the reality we perceive. But what about the absurd paths? The wild, looping, nonsensical journeys? Their arrows end up pointing in every conceivable direction, completely at random. When you add them all up, they cancel each other out into almost nothing. They are a cacophony of possibilities that fades into silence. So, the world we see, the single history we experience, isn't the only history. It's the result of an infinite number of histories interfering with each other. The most probable outcome is simply the one where the most possible paths constructively agreed. But deep down, baked into the fabric of reality, is the ghostly whisper of every other journey. Every path not taken is still part of the equation, a silent contributor to the one you are on right now. Sitix. The unreality of the past. Think of a memory. Any memory. The day you learned to ride a bike, maybe. The taste of your favorite childhood candy. You can picture it, right? You can almost feel it. But where is it that moment now? Not the memory of it, which lives in your brain, but the actual event. The objective reality of it. The uncomfortable answer is that it's nowhere. It has utterly ceased to exist. This is the core idea of presentism, the philosophical view that only the present moment is real. Your past isn't another country you can't visit, it's a country that has been wiped off the map. It's gone. All you have are fossils, the memories in your head, the photographs in an album, the scars on your skin. These are all artifacts that exist right now, in the present. They are echoes, not the shout itself. Imagine you are a boat moving across a perfectly still lake. The present is the boat itself, the only solid thing in the water. The past is the wake you leave behind. You can look back and see the pattern, the evidence that you were there. You can trace its shape and understand your journey. But you can never go back and sail in the wake. The wake isn't water you can travel on, it's just a disturbance, a memory that is already fading back into the stillness of the lake. Everything that has ever happened to you, your first word, your greatest triumph, your deepest regret, is now just information. It's a story you tell yourself in the present. The physical arrangement of atoms that constituted those moments has been completely disassembled and repurposed. The energy has scattered. The past you remember is a ghost, a reconstruction built in the here and now. And this has a strange implication for the many worlds we've been exploring. If only the present is real, then this moment, right now, is the bleeding edge of creation. The past, you recall, is just the singular path that led to this is present. But all those other potential pasts, the ones that branched off and created other versions of you, from your perspective, they are just as unreal as your own. They are all stories that have concluded, all wakes that have dissolved. The only thing that truly exists is this single, fleeting decision point of a moment before it too becomes just another ghost in the machine. 87. MWI and free will. You made a choice just now. The choice to listen. But in the infinite, branching garden of the many worlds interpretation, what does a choice even mean? According to MWI, at every quantum juncture, every moment a particle could be here or is there, the universe doesn't pick one. It splits, accommodating every single possibility in a separate, parallel world. And since your brain is a fantastically complex quantum system, This applies to you too. As you weigh a decision, coffee or tea, left turn or right, the universe doesn't wait for your answer. It simply splits. In one reality, you're now sipping coffee. In another, indistinguishable until that moment, you're enjoying tea. Both versions of you are equally real, each convinced they made the one true choice. This can feel like it erases free will entirely. If a version of you is doing everything you didn't do, did you really make a choice at all? Or are you just a passenger on one predetermined branch, experiencing an illusion of control while the grander cosmos plays out every possible script? But perhaps we're looking at it the wrong way. Maybe free will isn't the power to collapse all possibilities into a single reality. Maybe free will is the subjective experience of navigating your specific branch. Think of it this way: your consciousness is the thread that weaves one single continuous path through the multiverse. The feeling you call choice is the very act of your awareness committing to one timeline. The other yous on their paths are just as real, and their choices feel just as authentic to them. Your decision-making process, your memories, your values, your desires, is the engine that determines the character of your branch of reality. So, the many-worlds interpretation doesn't necessarily destroy free will, it redefines it. Your will isn't a chisel, carving a single statue from a block of marble, forcing all other possibilities to vanish. Instead, your will is a compass, guiding your unique journey across an infinite ocean of what could be. The choice you made to listen was profoundly real because it's the choice that created the path that brought you right here. 88. The mind dust problem. Where does your consciousness come from? We know your brain is made of atoms, carbon, oxygen, hydrogen. But none of those individual atoms are thinking. None of them feel joy or sadness. So how do you get the rich inner universe of yous from a collection of non-thinking, non-feeling particles? It's like trying to build a feeling out of bricks. One of the most elegant and ancient answers to this is a theory called panpsychism. The idea is simple. What if consciousness isn't something that magically appears when you arrange matter in a complex way, like in a brain? What if consciousness is a fundamental property of the universe itself? What if every single particle, every electron and quark has some tiny, unimaginably simple spark of experience? Not thinking or feeling like you do, but some primitive, raw proto-consciousness. In this view, consciousness isn't built. It was always there in everything. A fundamental feature of reality, just like mass or spin. But this beautiful solution creates its own profound problem. This is the mind dust problem, also known as the combination problem. If every particle has a tiny bit of mind dust, how do those trillions of tiny minds combine to create your single unified mind? Think about it like this. Imagine you have 1,000,000 specks of blue dust. Each speck is the experience of blueness. If you pile them all together, what do you get? You don't get the complex experience of seeing the ocean under a clear sky. You just get a giant pile of blueness. The individual experiences don't magically merge into a new, more complex one. They just sit next to each other. So how does the proto-consciousness in one neuron in your brain link up with the proto-consciousness of its neighbor to form a coherent thought? How does the experience of seeing the color red combine with the experience of hearing a sound to become your singular experience of watching a car drive by? No one knows. The theory suggests that your consciousness is built from these fundamental conscious bits, but it offers no explanation for how the dust of 1,000,000,000,000 tiny minds ever coalesces into the single, solid, continuous stream of awareness that you call yourself. It's a puzzle that leaves us wondering if our own minds are just a collection of disconnected sparks, or if the secret to our unity is something else entirely. Quantum Bayesianism, or cubism, proposes one of the most radical shifts in perspective we've encountered. It argues that quantum mechanics isn't a description of the world out there. Instead, it's a user's manual, a tool that helps you, a conscious agent, navigate the uncertainties of reality and make better bets on the future. In this view, the famous wave function, that cloud of probabilities, does not describe an electron itself. It describes your personal degree of belief about what you will experience if you interact with that electron. The quantum state is not in the world, it's in your head. It's a catalog of your expectations, shaped by your past experiences. This is where the Bayesian part comes in. Bayesian probability isn't about how often something happens in the long run. It's a measure of your individual confidence in a proposition. Think of a weather forecast. When a meteorologist says there's a 70% chance of rain, that 70% isn't a physical property of the sky. It's a statement of their belief, based on all the data they have. If you then look outside and see rain, the probability doesn't mysteriously collapse in the atmosphere. You simply update your knowledge. Your belief goes from 70% to 100%. The change happened within you, the observer. Cubism says the exact same thing happens in a quantum measurement. When a physicist measures an electron's spin, the wave function collapse isn't a violent physical event that ripples through the cosmos. It is simply the physicist updating their beliefs based on a new piece of information, the result of their experiment. The measurement problem vanishes because the collapse was never a physical process to begin with. It's a change in your personal knowledge. So, what is the world, according to Cubism? It's something real and independent, but something that quantum mechanics doesn't give us direct access to. The theory is not about what reality is, but about what you should expect to experience. Every measurement you make is a personal transaction with the universe. It's an act that creates a new, definite fact for you. In this deeply personal cosmos, you aren't a passive observer of a pre-written reality. You are an active participant, and the laws of quantum mechanics are your guidebook for the dance. 90. The participatory anthropic principle. This is the mind-bending idea that the universe, in a very real sense, might not exist until it is observed. It's not just that a tree falling in an empty forest makes no sound. The pap suggests the tree itself might not have been a definite, solid tree at all until a conscious mind was there to perceive it. This radical thought comes from one of the giants of physics, John Archibald Wheeler, and is rooted in the strangeness of quantum mechanics. At the subatomic level, a particle like an electron, when unobserved, isn't in one specific place. It's a fuzzy cloud of probabilities, a wave of potential. The very act of you measuring it forces this cloud to collapse into a single, definite point. Observation doesn't just discover reality, it seems to create it. Wheeler took this principle and scaled it up to the entire cosmos. He proposed that the universe is like a grand, self-observing system. It begins as an ocean of quantum uncertainty, a superposition of all possible histories. For billions of years, it evolves in this ghostly, probabilistic state. Then, life emerges. Consciousness flickers into being. And when that consciousness, when you looks out at the stars and traces the story back to the Big Bang, your observation acts like a cosmic measurement. Think of it like a video game where the world is only rendered when you look at it. The rest of the map exists only as code, as pure potential. In the PAP, your gaze reaches back in time, collapsing the wave function of the universe's entire history. Your act of looking at the cosmic microwave background now is what solidifies the Big Bang's existence then. The universe, in this view, waits for a participant to give its story meaning, to make it real. So, are there infinite versions of you? The participatory anthropic principle offers a different, perhaps even more profound perspective. It suggests that this version of you, right here, is not just a passive passenger on a cosmic journey. You are a fundamental co-creator. You are the universe's way of looking back at itself. And in that single act of looking, you transform the uncertain haze of potential into a concrete, shared reality. You are not just in the universe is, in a very real way, because of you. Tegmark's Level 4 Multiverse, the ultimate ensemble. This is the final level, the absolute bedrock of reality where the line between mathematics and existence completely dissolves. The idea is as simple as it is profound. Any universe that can be described by mathematics exists. All of them. Think of it like this. Our universe seems to run on a specific set of rules, a kind of cosmic operating system we call the laws of physics. But what if that's just one program running on an infinite cosmic computer? The Level 4 multiverse suggests that every single possible program, every self-consistent mathematical structure is also running physically real. It's not just universes with slightly different constants of nature. We're talking about universes with entirely different kinds of physics, different numbers of dimensions, and realities governed by mathematical rules so alien we can't even begin to imagine them. This is the mathematical universe hypothesis. It proposes that the reason mathematics is so unbelievably good at describing our universe is because our universe is a mathematical structure, and it's just one among an infinite ensemble of all possible structures. So, where are you in all this? Well, a mathematical structure describing a universe identical to ours, but where you made a different choice this morning is logically consistent. Therefore, it exists. A universe where you pursued your childhood dream and became an astronaut, that structure exists too. But it goes so much deeper. There are universes that are just chaotic seas of abstract geometry. There are realities that are simple, elegant equations existing as a complete cosmos unto themselves. In this ultimate library of being, most universes are utterly sterile and empty, or so bizarre they couldn't support anything resembling life. But by sheer infinite probability, an endless number of them are complex enough to contain self-aware substructures. Beings who, like you, look up at their sky and wonder if they are alone. The Level 4 multiverse is the ultimate statement of the Copernican principle. Not only are we not the center of our solar system, or our galaxy, or even our universe, we are inhabitants of just one mathematical possibility among an infinite sea of all possibilities. Our entire existence, every star, every galaxy, every thought you've ever had, is just one solution to an infinitely vast equation. A single, perfect sentence in a library containing every story that could ever be told. Mathematical Platonism. It's the unsettling and beautiful idea that math isn't something we invent, but something we discover. It proposes that numbers, perfect circles, and the theorems that govern them exist in their own reality. A timeless, abstract realm completely independent of our minds. You aren't an inventor when you do math. You are an explorer mapping a coastline that was always there. Consider the prime numbers. These lonely integers, divisible only by 1 and themselves. We didn't decide they should exist. They just do. And they follow strange, deep, and beautiful patterns that we are still struggling to understand, almost as if we're cosmic biologists studying the behavior of an abstract species. Or think about pi. Did we create the fact that a circle's circumference is always about 14 times its diameter? Or was that truth always waiting, encoded into the very definition of a perfect circle, long before any stars or planets formed? The Platonist argues that the Pythagorean theorem was true billions of years before Pythagoras was born to write it down. It was a fact of this other reality, waiting for a conscious mind to notice it. So where do these perfect truths live? Not in our physical universe. Every circle you draw is imperfect. Its line a little wobbly. But this idea of a circle, the pure mathematical form, exists in this Platonic realm. It's a reality of pure information, of perfect, unchanging concepts. It's not a place you can visit with a spaceship, but a landscape your mind can access through pure reason. Your consciousness becomes a telescope, peering into a universe made not of matter and energy, but of eternal logic. And here's the terrifying leap that connects to you and to the infinite. If these mathematical structures are fundamentally real, what if our entire universe is just one of them? This is the core of the mathematical universe hypothesis, the theory that our physical reality is as a mathematical structure. If you accept that, and you accept Platonism, then any self-consistent mathematical structure must exist just as surely as the number 2 exists. A universe governed by the equations of the manyworlds interpretation is no longer just a weird theory. It becomes an inevitable feature of this vast Platonic landscape, and within that structure, countless versions of you are not just possible, they are necessary, branching off at every quantum moment as the underlying math plays itself out. It forces you to ask, are you living in the one true reality? Or are you just one sentence on one page in an infinite mathematical library that has always existed? The mathematical universe hypothesis. This is the deepest, most mind-bending level of the multiverse iceberg. It's the radical idea that our physical reality isn't just described by mathematics, it is as a mathematical structure. Think about it like this. You're playing an incredibly advanced video game. To the characters living inside that world, everything feels solid and real. They experience their own laws of physics, cause and effect, the passage of time. But from your perspective, outside the screen, what is that world actually made of? It's pure information, code, a complex set of mathematical rules and relationships executing in real time. The characters are simply self-aware patterns running on that computational substrate. The mathematical universe hypothesis, or MUH, proposes that there are characters in that game. Our physical reality, from the smallest quark to the largest galaxy cluster, is nothing more than a giant, intricate mathematical object. There is no separation. The equations don't just model the reality, the equations are us the reality. You and I are simply the self-aware substructures, the complex patterns that have emerged within this cosmic calculation. Now, here is where it truly explodes into an infinite number of yous. If our universe is just one possible mathematical structure, what about all the other ones? The hypothesis states that every self-consistent mathematical structure that can possibly exist also exists as its own, equally real physical universe. Imagine a vast, abstract landscape of pure mathematics. In this landscape, you'll find structures that are simple, like the geometry of a perfect sphere. But you'll also find structures of near infinite complexity. And within that infinite set, there are countless structures complex enough to contain self-aware patterns like you. This is the ultimate multiverse. It doesn't just contain universes with slightly different physical constants. It contains universes with entirely different physics, different numbers of dimensions, maybe even different rules of logic. And in that endless library of realities, every possible version of your life, every choice you could have made, and every version of a you that could possibly be conceived of within a consistent mathematical framework is playing out right now. Your existence isn't a fluke. It's a mathematical inevitability, repeated an infinite number of times across the grand cosmic tapestry. 94. The computable universe hypothesis. This is the idea that the universe isn't just described by mathematics and physics, it fundamentally is a computation. It suggests that reality itself is the output of a vast cosmic computer processing information according to a specific set of rules, or an algorithm. The Big Bang wasn't just an explosion, it was the moment someone or something pressed run. Think of it like this. Imagine a simple computer program, like Conway's Game of Life. All it has are a few basic rules applied to pixels on a grid. Rules about birth, survival, and death. Yet, when you run it, you see incredibly complex, unpredictable, and lifelike patterns emerge from that simple code. They move, they evolve, they interact. Now, scale that up. The computable universe hypothesis proposes that our reality is a far more sophisticated version of this. The fundamental particles are the pixels, and the laws of physics are the simple, underlying rules. Everything else, galaxies, stars, planets, and even you, is an emergent pattern. This means every single moment of your life is a state of the universal computer. The state of the universe one Planck time ago was the input, and the laws of physics were the algorithm that computed the state of the universe right now. Your thoughts, your feelings, your very consciousness are unimaginably complex patterns running on this cosmic hardware. There is no distinction between the simulation and the reality, because the reality is the simulation. And here is where it connects to the infinite. If our universe is just one possible program, running on one cosmic machine, what's to stop other programs from running? If the fundamental reality is information, then any possible computable set of rules could constitute its own universe. Somewhere, another program is running that is almost identical to ours, but with one single bit of information flipped. In that reality, a version of you exists who took the other job, who said what they wished they'd said, who turned left instead of right. An infinite library of cosmic source codes, each one generating its own unique reality, its own unique version of you. 95. The Boltzmann brain problem. Take a moment and think of your most cherished memory. Feel it. See it. Now, what if I told you that memory is a complete fabrication? That you and your entire consciousness just flickered into existence a moment ago, fully formed, with a lifetime of memories that never actually happened? This is the unnerving core of the Boltzmann brain problem, a paradox that haunts the edges of cosmology. It begins with the fundamental law of the universe, entropy. Everything tends towards disorder. A sandcastle crumbles into sand. A star burns out into cold gas. The ultimate fate of our universe is predicted to be a state of maximum disorder, a vast, uniform, and eternal thermal equilibrium known as heat death. Nothing happens. Forever. Except, not quite. In the endless expanse of a dead universe, over timescales that make the current age of the cosmos seem like a nanosecond, random quantum fluctuations will inevitably occur. It's pure statistics. If you leave a million monkeys typing for eternity, one will eventually produce Hamlet. Similarly, in an eternal cosmic soup, particles will randomly bump into each other in just the right way to create something complex. And here is the terrifying calculation. What is the absolute minimum structure required to have a conscious thought, like the one you're having right now? A single, isolated human brain. Statistically, it is monumentally, incomprehensibly more likely for a random fluctuation to assemble a solitary brain than it is to assemble our entire, sprawling, low-entropy universe with its billions of galaxies and billions of years of history. This spontaneously formed entity is a Boltzmann brain. It would pop into being, experience a single, vivid thought, perhaps believing it was you, living your life, remembering your past. Then, just as quickly, it would dissolve back into the chaotic void. The paradox is this. If our current theories about the universe's future are correct, then the overwhelming majority of conscious observers in existence should be these fleeting phantom brains. They should outnumber real people like us by an almost infinite margin. So, look at your hands. Trust your memories. How can you be so sure you're the real deal, and not just the universe dreaming for a second? The simulation hypothesis. It's the unsettling idea that our entire universe, from the farthest galaxy to the very thoughts inside your head, is an artificial reality, a computer program of unimaginable complexity. Think about the video games you've played. 30 years ago, they were simple blocks and pixels. Today, they are photorealistic worlds, populated by characters with their own routines and desires. Now, project that technological growth forward. 1,000 years. 1,000,000. What kind of reality could a civilization that advanced create? Would it be distinguishable from a base physical reality? The philosopher Nick Bostrom argued that one of three things must be true. Any advanced civilization goes extinct before developing the technology to create these ancestor simulations. Play. They develop the technology, but for some ethical or practical reason, they lose interest and never run them. Or 3. They run billions upon billions of these simulations, meaning the number of simulated consciousnesses, like you, would vastly outnumber the real ones in the base reality. If that's the case, basic probability suggests we are almost certainly living inside one of them. You start to look for clues. Glitches in the matrix. Why are the fundamental constants of our universe, the speed of light, the force of gravity, so exquisitely fine-tuned to allow for life? Was it a cosmic coincidence? Or did a programmer just set the parameters? At the smallest possible scale, the Planck length, space itself, seems to stop being smooth and continuous. It becomes granular, pixelated. Is that the resolution limit of our cosmic computer screen? And what does that make you? Are you the player, experiencing this world through an avatar? Or are you a sophisticated non-player character, an NPC, whose entire existence is just a string of code? Your feelings of love and loss just complex subroutines? It doesn't necessarily mean your life is meaningless. The simulation can be so perfect that your experiences are completely authentic to you. The joy you feel is real. The pain is real. The code is just that good. But it does raise a chilling question. If your reality is a program being run on some cosmic hard drive, could someone or something simply decide to shut it down? Or worse, could there be other copies of you running in other simulations at the very same time? 9-7. Philosophical zombies in parallel worlds. Look at the person closest to you. Or just think about them. They laugh, they cry, they talk about their dreams. But how do you know there's an inner life behind their eyes? How do you know they aren't just a perfect imitation, a biological machine executing a flawless program? This is the unnerving thought experiment of the philosophical zombie. A P-zombie is a hypothetical being that is physically and behaviorally identical to a conscious human in every single way. Imagine a perfect replica of you. It goes to your job, laughs at your friends' jokes, and even says I love you to your family with what appears to be genuine emotion. It would tell you with perfect sincerity that it feels joy and sorrow. But on the inside, there's nothing. No subjective experience. No qualia. No what it's like to be them. Just an incredibly complex algorithm perfectly mimicking life. The lights are on, but absolutely nobody is home. You can't prove they exist, but more importantly, you can't prove they don't. You only have direct access to one mind in the entire universe, your own. Now, let's connect this to the staggering scale of the multiverse. The many worlds interpretation suggests that anything that can happen does happen in some parallel branch of reality. So, the critical question is it physically possible for a universe to exist that is an atom for atom copy of our own, but where the strange emergent property of consciousness simply failed to ignite? If the answer is yes, then that universe, a dark, empty twin of our own, almost certainly exists. An entire parallel Earth populated by your friends, your family, and even a copy of you, all going through the motions with flawless precision. This would imply that consciousness isn't an inevitable result of complex brain chemistry. It's something extra, a ghost in the machine that doesn't have to be there. And here's the final turn of the screw. Across the infinite multiverse, could there be a branch where your exact physical body formed it's living your life right now, but the you that is listening to this never woke up inside of it? A perfect actor playing the part of you with no one on the inside to watch the show. And from the outside, no one could ever tell the difference. 98. Hilbert Space. This isn't a place you can visit. It's not in our universe, because, in a way, it is the universe's playbook. Think of it as the ultimate cosmic stage, an abstract space where every single possible state of a quantum system exists all at once. Imagine you're trying to describe a single particle. In our world, you'd give its position and momentum. Simple. But in the quantum world, that particle exists in a ghostly superposition, a blend of all its potential positions and momentum simultaneously. So, where do you keep track of all these infinite possibilities? You track them in Hilbert space. Think of it like a room with an infinite number of dimensions. Each dimension doesn't represent left, right, or up, down. Instead, each dimension represents one possible outcome, one dimension for the particle being here, another for it being over there, another for it spinning this way, another for it spinning that way. The state of the actual particle, its wave function, is a single arrow or vector, pointing somewhere within this infinite dimensional room. Its direction tells you the precise recipe, the exact mix of all the possibilities that describe the particle at that moment. Now, here's where it gets truly wild and connects to the idea of infinite use. According to the many worlds interpretation, when you make a measurement, when you look at the particle and force it to choose a state, the arrow doesn't just snap to one dimension. The universe itself doesn't collapse. Instead, the entire universe, including you, splits. It branches off, following different paths through the Hilbert space. In one branch, the arrow points along the particle is here dimension, and that's the reality that version of you experiences. In another branch, it points along the particle is their dimension, and a different you experiences that. The Hilbert space is the mathematical framework that contains the blueprint for every single one of these branches. It's the pre-existing ocean of potential from which all parallel realities emerge. It's the ultimate evidence that, mathematically at least, there isn't just one you. There is a vector in an infinite dimensional space, and every possible you is just one of its many, many projections. Guide 9. The good old universe. Imagine a universe where time travel into the past isn't just possible, it's an inevitable consequence of traveling far enough. This isn't a paradox from a sci-fi novel. It's a bizarre, yet mathematically sound, solution to Einstein's own equations of general relativity. It was discovered by the brilliant reclusive logician Kurt Gödel. As a gift for his friend Albert Einstein, Gödel decided to play in the sandbox of space-time physics, and what he found was profoundly disturbing. He described a universe that obeyed all of Einstein's rules, but with one crucial difference. The entire cosmos was gently, but uniformly, rotating. Think of space-time as a vast, flowing river. In our intuition, that river flows in one direction, forward, into the future, but in Gödel's universe, the cosmic rotation drags the river of spacetime along with it, creating a giant, slow-motion whirlpool. If you were to get in a spaceship and travel on a large enough circular path, you wouldn't just be moving through space. You'd be riding a current in spacetime itself. This path is called a closed, time-like curve. By completing this cosmic lap, you could arrive back at your starting point in space, but at a moment in time before you even left. The consequences are reality-shattering. In a Gödel universe, the past is never truly gone. Causality, the fundamental rule that a cause must precede its effect, completely evaporates. There is no objective before or after on a cosmic scale. You could, in theory, witness your own birth or have a conversation with your great-grandmother when she was a child. The arrow of time is broken. So, do we live in one? All of our observations suggest no. Our universe is expanding, not rotating. But the fact that the Gödel universe is a valid possibility within the laws of physics is what makes it so haunting. It's a ghost in the machine of reality, a mathematical proof that our intuitive sense of a linear timeline, a fixed past, and an open future is not a logical necessity. It may just be a local feature of our particular cosmic neighborhood, a gentle current in an ocean where terrifying whirlpools are allowed to exist. 100. The edge of understanding. This is the part of the map where ancient cartographers would simply write, "Here be dragons." It's not a place of monsters, but a frontier where our most powerful tools, our language, our mathematics, our very intuition begin to fail us. They were forged for survival in one world, not for comprehending all of them. Everything we've explored, from quantum branching to the infinite library of your possible lives, has been navigated using the logic of our universe. But what happens when the logic itself becomes the subject of inquiry? Imagine trying to understand the concept of wetness if you were a creature made entirely of water. You're inside the system you're trying to describe. Our brains are exquisitely tuned to dodge predators and find fruit, not to conceptualize what lies beyond the Big Bang or what laws might govern the creation of physical laws themselves. Here, at the edge, the questions become untethered. Is the multiverse all there is? Or is it just one bubble in a cosmic foam we can't perceive? Is there a base, reality, a trunk from which all other branches grow? Or is it an endless, rootless ocean of possibilities? If every version of you exists, what does that make the consciousness listening to my voice right now? Are you just one frame in a cosmic film, an arbitrary focal point for a single timeline? We search for a why behind the quantum foam, but that might be like asking why a circle is round. The question itself might be a category error, a ghost of our limited, linear perspective. This is the ultimate confrontation with infinity. It's the realization that the search for other yous was never really about finding them. It was about understanding the staggering, incomprehensible nature of the engine that generates them all. You are not just a leaf on a branch of a cosmic tree. The system implies you are the tree and the entire forest. Each choice, each breath, each thought is not just your experience, but one valid iteration of a universal process playing itself out through the vessel of your identity. The edge of understanding isn't a wall. It's a horizon. It's the quiet, humbling awe that settles in when you stare into the abyss and realize it isn't empty, but filled with a structure so vast and complex that seeing it isn't the point. The point is simply to know that it's there. This is where physics becomes a form of meditation, and the question, is there an infinite number of me's? Finally dissolves into a deeper, silent peace.